Welcome to Stellar Worlds. Did you know that beyond our home planet, there are trillions of fascinating worlds waiting to be discovered? From scorching hot giants of liquid metal to icy realms with deep oceans, and potentially even havens for life, each exoplanet tells a unique story. Join us as we dive into the most intriguing planets in the universe, right here on Stellar Worlds. Let's explore the universe together. Are you ready? Let's begin. For our first world today, we're warping on over to LHS 1140c, a super-Earth in a remarkable multi-planet system. 40 light-years from Earth, close enough that light from this star began its journey during the Reagan presidency. A remarkable planetary system orbits a small red dwarf star. The system hosts at least 2 planets, including LHS 1140c, a super-Earth 1.8 times Earth's radius orbiting every 3.8 days. But LHS 1140c isn't the star of this system. That honor belongs to its sibling, LHS 1140b, one of the most promising potentially habitable planets ever discovered, now a top target for the James Webb Space Telescope's search for signs of life beyond Earth. This is the story of LHS 1140c, a planet discovered in the shadow of its more famous companion, yet scientifically valuable in its own right, revealing how multi-planet systems form around the most common stars in our galaxy. A super-Earth discovered in 2017 orbiting one of our nearest stellar neighbors, an M-dwarf star just 40 light-years away. This planet is part of the LHS 1140 system, which has become one of the most intensely studied nearby planetary systems because it hosts LHS 1140b, a super-Earth in the habitable zone that might have conditions suitable for liquid water and possibly even life. But while LHS 1140b gets most of the attention, and deservedly so as a potentially habitable world, LHS 1140c is fascinating in its own right. It's a hot super-Earth orbiting every 3.8 days, providing crucial context for understanding the system's architecture, formation history, and dynamical evolution. And studying both planets together reveals patterns about how planetary systems form around M-dwarf stars, the most common type of star in our galaxy. The LHS 1140 system was discovered by the embark project, an array of small robotic telescopes specifically designed to search for transiting planets around nearby M-dwarfs. By focusing on our nearest stellar neighbors, embark identifies the best targets for detailed atmospheric characterization and long-term study. LHS 1140 is one of Earth's greatest successes, revealing a multi-planet system around a stable, quiet M-dwarf close enough for detailed observations. LHS 1140 itself is an M4.5 dwarf star, much smaller, cooler, and dimmer than our Sun, but also much longer-lived. At about 5 billion years old, LHS 1140 is roughly the same age as our Sun, but will continue burning hydrogen for trillions of years, giving any planets in its habitable zone vastly longer timescale for life to develop and evolve than Earth has experienced. Today we're going to explore how the embark project operates and why it focuses on nearby M-dwarfs, how LHS 1140c was discovered alongside its more famous sibling, what LHS 1140c's characteristics tell us about hot super-Earths, how it compares to LHS 1140b and provides context for understanding the system, why multi-planet systems around M-dwarfs matter for astrobiology, and what future observations might reveal about this nearby planetary system. Let's discover a super-Earth in one of our cosmic neighborhood's most interesting planetary systems. Chapter 1. The Earth Project. LHS 1140c was discovered by the embark project, a dedicated survey searching for transiting planets around our nearest M-dwarf neighbors. The embark project, which stands for M-Earths, planets around M-dwarf stars, began operations in 2009 with a focused mission: find transiting planets around the nearest and brightest M-dwarfs. The project operates two arrays of robotic telescopes: M-Earth North at the Fred Lawrence Whipple Observatory in Arizona, and M-Earth South at Cerro Tololo Inter-American Observatory in Chile. Each M-Earth array consists of 8 40-centimeter telescopes, modest by professional standards, but perfectly sized for monitoring bright nearby stars. The telescopes observe automatically every clear night, monitoring about 2,000 nearby M-dwarfs with extreme precision, searching for the periodic dimming that indicates transiting planets. Why focus specifically on M-dwarfs? Several reasons make them ideal targets for finding potentially habitable planets. First, M-dwarfs are small, typically 20 to 60% the Sun's diameter, so planets create larger, more easily detectable transit signals. A Earth-sized planet transiting an M-dwarf might block 1% of the star's light, compared to 0.01% for the same planet transiting a Sun-like star. Second, M-dwarfs are the most common stars in the galaxy, accounting for about 70 to 80% of all stars. If we want to understand typical planetary systems, we need to understand planets around M-dwarfs. Third, the habitable zone around cool M-dwarfs is very close, typically 0.1 to 0.3 AU, meaning planets in the habitable zone have short orbital periods of 10 to 50 days. Short periods mean frequent transits, allowing quick discovery and confirmation. Fourth, nearby M-dwarfs are bright enough for detailed follow-up observations despite being intrinsically faint. The nearest M-dwarfs are among the brightest targets for atmospheric characterization, even though they're hundreds of times dimmer than the Sun. The M-Earth strategy is simple but powerful. Monitor the nearest, brightest M-dwarfs with sufficient precision to detect Earth-sized planets, then extensively characterize any discoveries with the world's largest telescopes and space observatories. This approach has proven extraordinarily successful, with M-Earth discovering several of the best-studied transiting exoplanets, including LHS 1140b and its companion LHS 1140c. The project operates robotically, with telescopes observing automatically based on weather conditions and target visibility. Each clear night, the telescopes photograph their target stars repeatedly, building up high-precision light curves that reveal transiting planets. Automated pipelines analyze the data in near real time, flagging promising signals for human review. When M-Earth detects a potential planet, extensive follow-up confirms the discovery. High-resolution imaging verifies the target is a single star. Spectroscopy characterizes the star precisely. Additional photometry from other facilities confirms the transit signal. And for the most interesting targets, radial velocity observations measure the planet's mass, determining density and composition. Chapter 2. The Discovery. The discovery of the LHS 1140 system unfolded in stages, with LHS 1140 be found first and LHS 1140c revealed through careful analysis of the same data. In late 2014, M-Earth South detected periodic transit signals from LHS 1140 indicating a planet with about 1.6 Earth radii orbiting every 25 days. This was LHS 1140b, which immediately attracted intense interest because its orbital period placed it squarely in the star's habitable zone, the region where temperatures allow liquid water on a planet's surface. The Discovery team conducted extensive follow-up observations throughout 2015 and 2016. High-resolution imaging from large telescopes confirmed LHS 1140 is single. Spectroscopy characterized the star as an M 4.5 dwarf with mass 0.15 solar masses. And crucially, radial velocity observations from multiple spectrographs, including HARPS at La Silla Observatory, measured LHS 1140b's mass at approximately 6.6 Earth masses. Combined with the radius of 1.7 Earth radii, this gave a density of about 7 grams per cubic centimeter, significantly denser than Earth's 5.5 grams per cubic centimeter. This high density indicates LHS 1140b is rocky with a large iron core, making it an excellent candidate for a potentially habitable rocky planet. The discovery of LHS 1140b was announced in April 2017 in the journal Nature, immediately generating enormous excitement. Here was a rocky planet in the habitable zone of a nearby, quiet star, one of the best potentially habitable exoplanet discoveries ever made. But during the extensive photometric observations and radial velocity measurements, the team noticed additional signals. The M-Earth light curve showed hints of additional transit-like features at a period of about 3.8 days. The radial velocity data, while dominated by the 25-day signal from LHS 1140b, showed residual variations consistent with an additional planet. Further analysis confirmed these signals came from a second planet, LHS 1140c. With a radius of approximately 1.81 Earth radii and a 3.78-day orbital period, LHS 1140c was announced alongside LHS 1140b in the 2017 Nature paper as part of a multi-planet system. The radial velocity data allowed mass measurement for LHS 1140c, yielding approximately 1.8 Earth masses, though with significant uncertainty due to the smaller signal compared to the more massive LHS 1140b. This gave an estimated density around 2 to 3 grams per cubic centimeter, lower than LHS 1140b's density, but consistent with a rocky composition, possibly with more volatile content or a small hydrogen-helium atmosphere. The discovery was scientifically valuable for several reasons. First, it revealed LHS 1140 hosts a multi-planet system, not just a single planet. Multi-planet systems provide crucial constraints on formation and migration because the planet's orbital configurations preserve information about their dynamical history. Second, having both a hot inner planet and a potentially habitable outer planet allows comparative studies. How do two planets in the same system around the same star develop such different conditions? What does this tell us about atmospheric retention, volatile delivery, and habitability? Third, the system architecture, with planets at 3.8 and 25 days, is relatively common around M dwarfs, suggesting the LHS 1140 system is representative of a typical planetary system around these stars. Chapter 3. Characteristics of LHS 1140c. Let's examine LHS 1140c's characteristics in detail, because they place it in an interesting position as a hot super-Earth in a system with a potentially habitable companion. LHS 1140c is classified as a super-Earth. Planets larger than Earth but smaller than Neptune, typically in the range of 1.25 to 2 Earth radii. At 1.81 Earth radii, LHS 1140c sits comfortably in this category, being about 81% larger in diameter than Earth. The physical characteristics are reasonably well determined from combined transit and radial velocity observations. The radius is 1.81 Earth radii from transit depth. The mass is approximately 1.81 Earth masses from radial velocity measurements, though this has substantial uncertainty. If this mass is accurate, it gives a density around 2 to 3 grams per cubic centimeter. This density is significantly lower than Earth's 5.5 grams per cubic centimeter and much lower than LHS 1140b's 7 grams per cubic centimeter. The lower density could indicate several possibilities: a rocky planet with lower iron content, a rocky core with a substantial water layer, or a rocky core with a thin hydrogen-helium atmosphere. At 1.8 Earth radii, LHS 1140c sits right around the radius valley. The observed gap in the planetary radius distribution around 1.5 to 2 Earth radii, where photoevaporation is thought to strip atmospheres from planets below a mass threshold. Whether LHS 1140c retained a primordial hydrogen atmosphere or lost it to photoevaporation is an open question that better mass measurements and atmospheric observations could resolve. The orbital characteristics are precisely known from years of transit observations. The orbital period is 3.78 days, less than 4 Earth days per year. The semi-major axis is approximately 0.028 AU, which is about 4.2 million kilometers or 2.6 million miles. To put this in perspective, Mercury orbits the Sun at 0.39 AU. LHS 1140c orbits about 14 times closer to its star than Mercury does to ours. However, because LHS 1140 is a cool M dwarf much dimmer than the Sun, the stellar flux received by LHS 1140c is more comparable to Mercury's environment rather than being even more extreme. At this distance, LHS 1140c is certainly tidally locked, with one hemisphere permanently facing the star. The orbital velocity is approximately 100 kilometers per second. The orbital eccentricity is very low, essentially zero, meaning the orbit is circular, typical for planets in such close orbits where tidal forces rapidly circularize orbits. The equilibrium temperature is estimated at approximately 700 Kelvin, or about 427 degrees Celsius or 800 degrees Fahrenheit. This is hot, much too hot for liquid water, but not as extreme as many hot Jupiters exceeding 1,500 Kelvin. At 700 Kelvin, rocky surfaces would be hot enough to glow faintly red, water would be steam, and atmospheric dynamics would be vigorous. The host star LHS 1140 is an M4.5 dwarf, a cool, small, dim red dwarf. The stellar mass is approximately 0.146 solar masses, less than 1/7 the Sun's mass. The radius is about 0.21 solar radii, making it roughly 1/5 the Sun's diameter, similar in size to Jupiter. The temperature is approximately 3,100 Kelvin, much cooler than the Sun's 5,778 Kelvin. The age is estimated at approximately 5 billion years, similar to the Sun's 4.6 billion years. However, M dwarfs live for trillions of years, so LHS 1140 is still in its early to middle age despite being older than the Sun in absolute terms. The metallicity appears roughly solar, indicating similar abundances of elements heavier than hydrogen and helium compared to the Sun. The distance from Earth is 40 light years, remarkably close in galactic terms, making LHS 1140 one of the nearest known planetary systems. Chapter 4. The Multi-Planet Context. Understanding LHS 1140c requires understanding it as part of a multi-planet system with a potentially habitable LHS 1140b. The LHS 1140 system's architecture is fascinating. 2 confirmed planets orbit at 3.8 and 25 days, both on nearly circular orbits in the same plane. This configuration is common around M dwarfs and provides clues about system formation and evolution. LHS 1140b, the outer planet, is the more massive at 6.6 Earth masses and 1.7 Earth radii. With a density around 7 grams per cubic centimeter, it's a dense rocky planet with a large iron core. Its 25-day orbit places it in the conservative habitable zone where temperatures could allow liquid water if the planet has an atmosphere. LHS 1140c, the inner planet, is less massive at approximately 1.8 Earth masses and 1.81 Earth radii. The lower density around 2 to 3 grams per cubic centimeter suggests different composition, either less iron-rich, water-rich, or with a thin atmosphere. Why do these 2 planets in the same system have such different properties? Several factors might contribute. First, they formed at different locations in the protoplanetary disk, possibly experiencing different temperatures, solid surface densities, and volatile availability. LHS 1140c formed closer where temperatures were higher, potentially affecting its composition. Second, they experienced different levels of stellar irradiation throughout their histories. LHS 1140c, receiving much more stellar flux at 0.028 AU, might have lost atmospheric volatiles to photoevaporation, while LHS 1140b at 0.088 AU retained its atmosphere. Third, accretion stochasticity, random variations in what material planets accumulate during formation, might have created compositional differences even if both planets formed from similar initial conditions. The system architecture suggests both planets likely formed near their current locations rather than undergoing extensive migration. The circular orbits and coplanar configuration indicate a dynamically calm system without violent planet-planet scattering. This is consistent with in-situ formation or gentle disk-driven migration that didn't disrupt the system. Some models suggest both planets might have migrated inward modestly from initial formation locations beyond 1 AU, with migration stopping when the protoplanetary disk dissipated. But the lack of highly eccentric orbits or significant mutual inclinations suggests any migration was gentle and orderly. The fact that LHS 1140 hosts multiple planets matters for understanding the system's history and predicting additional companions. Statistical studies show that planetary systems are rarely populated by single planets. Where there's one planet, there are often more. The LHS 1140 system might host additional planets at wider separations not yet detected. Long-term monitoring might reveal additional planets through transit timing variations, subtle changes in when LHS 1140b and C transit caused by gravitational perturbations from unseen companions. Radial velocity observations might detect longer-period planets through their gravitational influence on the star. And future direct imaging might photograph any massive planets at wide separations. Chapter 5. Habitability Assessment. Let's address habitability for LHS 1140c specifically, though the answer is straightforward. At 700 Kelvin equilibrium temperature, LHS 1140c is far too hot for liquid water on any surface. The planet orbits well inside the habitable zone, which for LHS 1140 extends from approximately 0.07 to 0.13 AU. At 0.08 AU, LHS 1140c is about 2.5 to nearly 5 times closer than the inner edge of the habitable zone. At these temperatures, any water exists as steam. Rocky surfaces would be extremely hot, possibly partially molten depending on composition. Tidal locking creates extreme day-night temperature contrasts unless atmospheric circulation efficiently redistributes heat. And the intense stellar radiation and potential stellar flares from the active young M dwarf would make conditions hostile to life as we know it. However, LHS 1140c's scientific importance for astrobiology lies in its role as part of a system with the potentially habitable LHS 1140b. By studying both planets comparatively, we learn about atmospheric retention, volatile distribution, and the factors determining which planets maintain conditions suitable for life. If LHS 1140b has an atmosphere supporting liquid water, making it potentially habitable, while LHS 1140c lost its atmosphere to photoevaporation or never developed one. This reveals the critical threshold for atmospheric retention around M dwarfs. This knowledge applies to predicting which planets around other M dwarfs might be habitable. Conversely, if both planets retained atmospheres despite their different orbital distances and stellar flux levels, it suggests atmospheric retention around quiet M dwarfs is more robust than some models predict, improving prospects for habitability in many systems. The broader context is that M dwarfs host the majority of potentially habitable real estate in the galaxy. Understanding planetary systems around M dwarfs including systems like LHS 1140 with both hot and temperate planets, is essential for assessing where life might exist beyond Earth. Chapter 6: Scientific Significance. Why does LHS 1140c matter for exoplanet science beyond its famous habitable zone sibling? LHS 1140c contributes to several research areas. First, multi-planet system architecture around M dwarfs. Understanding how multiple planets coexist in systems around the most common stars reveals formation processes and dynamical evolution pathways typical of most planetary systems in the galaxy. Second, hot super-Earth population studies. LHS 1140c is one of many hot super-Earths around M dwarfs, and characterizing these planets statistically reveals patterns in mass, radius, density, and composition that test formation and evolution theories. Third, atmospheric retention at the radius valley. At 1.8 Earth radii, LHS 1140c sits near the radius valley where photoevaporation strips atmospheres. Determining whether it retained hydrogen-helium or lost it tests photoevaporation models specifically for M dwarf hosts. Fourth, comparative planetology within single systems. Comparing LHS 1140c and B reveals how planets in the same system develop differently based on orbital distance, formation location, and stellar irradiation history. Fifth, nearby target accessibility. At 40 light-years with a relatively bright host star for an M dwarf, the LHS 1140 system is accessible for detailed long-term study, providing a nearby laboratory for understanding M dwarf planetary systems. Chapter 7: Future Research. What's next for studying LHS 1140c and its remarkable planetary system? The LHS 1140 system is a top priority for current and future observations, primarily focused on LHS 1140b's potentially habitable conditions, but also providing opportunities to study LHS 1140c. The James Webb Space Telescope has observed or will observe LHS 1140b extensively as one of the best potentially habitable planet targets. While JWST focuses on LHS 1140b, these observations might also constrain LHS 1140c's properties if both planet signals can be separated in the data. Improved radial velocity measurements could refine LHS 1140c's mass, reducing current uncertainties and enabling precise density calculation that would resolve whether the planet is purely rocky, water-rich, or has a thin atmosphere. Long-term transit timing observations over decades might detect additional planets through gravitational perturbations or reveal dynamical interactions between LHS 1140b and C. If LHS 1140c has retained an atmosphere, transmission spectroscopy during transits could detect molecules revealing atmospheric composition, though the small planetary radius and modest atmospheric scale height make this challenging. Future ground-based, extremely large telescopes might enable higher precision observations, clarifying both planets' properties and searching for additional companions at wider separations. Chapter 8: Conclusion. Let's recap what makes LHS 1140c scientifically important. LHS 1140c is a hot super-Earth with 1.81 Earth radii and approximately 1.8 Earth masses orbiting every 3.8 days at 0.028 AU from an M dwarf star 40 light-years away. With temperatures around 700 Kelvin, it's too hot for habitability, but scientifically valuable as part of a multi-planet system, including the potentially habitable LHS 1140b. Discovered by the M-Earth project in 2017 alongside its more famous sibling, LHS 1140c reveals how planetary systems form around M dwarfs, the most common stars in our galaxy. The system's architecture, with two planets on circular orbits at different distances, provides insights into formation, migration, atmospheric retention, and the factors determining planetary habitability. While LHS 1140b rightfully attracts most attention as one of the best potentially habitable exoplanet discoveries, LHS 1140c matters as essential context for understanding the system. By comparing the two planets, we learn what makes some world habitable while others aren't, knowledge applicable across countless M-dwarf systems filling our galaxy. 40 light-years away, LHS 1140c continues its rapid orbit, completing 96 circuits per Earth year around a cool red dwarf. One hemisphere faces the star, heated to 700 Kelvin. The other knows only darkness. Between these extremes, atmospheric circulation might redistribute heat if an atmosphere exists. Meanwhile, farther out in the same system, LHS 1140b orbits in the habitable zone where conditions might support liquid water and conceivably life. The James Webb Space Telescope is observing it now, searching for signs of an atmosphere, water vapor, perhaps even biosignatures. LHS 1140c may never achieve the fame of its potentially habitable sibling, but it plays a crucial role in the system's story, revealing how planets form, evolve, and develop the conditions that might or might not support life. The LHS 1140 system exemplifies why we study planetary systems holistically, not just focusing on potentially habitable worlds. Every planet teaches us something. Hot super-Earths like LHS 1140c reveal atmospheric retention processes. Potentially habitable worlds like LHS 1140b show where life might exist. Together, they reveal the full spectrum of planetary outcomes and systems around the most common stars in our galaxy. For our next planet today, we're checking out HAT P26b, the Neptune with a surprisingly clear sky. 437 light-years from Earth, a planet the size of Neptune orbits its star every 4 days. When astronomers pointed the Hubble Space Telescope at HAT P26b in 2016, they expected to see what most Neptune-sized planets show: a hazy, cloudy atmosphere obscuring the chemical signatures beneath. Instead, they found something remarkable, one of the clearest atmospheres ever observed on an exoplanet, revealing water vapor in unprecedented detail. This discovery transformed HAT P26b from just another warm Neptune into one of the most scientifically valuable planets for understanding atmospheric chemistry, cloud formation, and the surprising diversity of planetary atmospheres across our galaxy. A warm Neptune discovered in 2010 by the Hungarian-made Automated Telescope Network that became famous in 2017 when Hubble observations revealed it has one of the clearest, most transparent atmospheres of any exoplanet ever studied. Before we dive in, I need to clarify a common misclassification. HAT P26b is often called a hot Jupiter in older sources, but it's actually a warm Neptune, significantly smaller than Jupiter with about Neptune's radius, but orbiting much closer to its star than Neptune does to our Sun. This distinction matters because Neptune-sized planets have very different atmospheric properties, formation histories, and scientific significance compared to Jupiter-sized giants. What makes HAT P26b extraordinary isn't its size or temperature. Many similar warm Neptunes are known. What sets it apart is its atmosphere. Most Neptune-sized exoplanets observed to date show flat, featureless transmission spectra suggesting high-altitude clouds or hazes blocking our view of deeper atmospheric layers. But HAT P26b's atmosphere is remarkably clear, allowing detection of strong water vapor features and revealing atmospheric composition in detail impossible for most planets of this size. This clarity has made HAT P26b one of the best-studied Neptune-sized exoplanets and a benchmark for understanding atmospheric chemistry on planets smaller than Jupiter. The discovery that this planet's atmosphere is unusually transparent raised profound questions. Why is HAT P26b's atmosphere clear when similar planets are cloudy? What does this tell us about atmospheric physics and cloud formation? And what can we learn from this exceptional planet about the diversity of planetary atmospheres? Discovered by the HATNet survey, one of the most successful ground-based planet detection programs, and extensively characterized by Hubble, Spitzer, and ground-based telescopes. HAT P26b exemplifies how continued observation of individual planets reveals unexpected diversity, forcing us to rethink our understanding of planetary atmospheres. Today we're going to explore how HATNet operates and why it's been so successful, how HAT P26b was discovered and initially characterized, what its physical properties tell us about warm Neptunes, why its clear atmosphere is so scientifically valuable and surprising, what atmospheric observations have revealed about its composition and chemistry, how it compares to other Neptune-sized planets, and what this reveals about atmospheric diversity, and what future observations might teach us. Let's discover the Neptune-sized planet with surprisingly clear skies. Chapter 1. The HATNet Project. HAT P26b was discovered by HATNet, the Hungarian-made automated telescope network, one of the pioneering ground-based transit surveys. HATNet, established in 2003, pioneered the use of small, wide-field automated telescopes to search for transiting exoplanets. The network operates from two sites, the Fred Lawrence Whipple Observatory in Arizona and Mauna Kea Observatory in Hawaii, providing coverage of both northern and southern skies. Each HATNet station uses small telephoto camera lenses, only 11 centimeters in aperture, mounted on fully automated systems that observe every clear night. Despite their modest size, these telescopes monitor enormous areas of sky simultaneously, observing hundreds of thousands of stars looking for the periodic dimming that indicates transiting planets. The HATNet strategy exemplifies how smart design and persistent observation can compete with much larger telescopes. By monitoring very large sky areas and focusing on relatively bright stars, HATNet identifies planets around stars bright enough for detailed follow-up spectroscopy, exactly the targets needed for atmospheric characterization. The name HAT stands for Hungarian-Made Automated Telescope, reflecting the project's origins at the Konkoly Observatory of the Hungarian Academy of Sciences and later partnership with the Harvard-Smithsonian Center for Astrophysics. The project has discovered over 50 transiting exoplanets, many around relatively bright stars suitable for detailed study. HATNet's observing strategy is systematic and persistent. Night after night, the telescopes photograph their target fields, building up light curves showing each star's brightness over weeks and months. Automated pipelines search these light curves for periodic dimming consistent with transiting planets. Promising signals are flagged for follow-up observations confirming the planet and measuring its properties. The project's success demonstrates that exoplanet discovery doesn't require the largest, most expensive telescopes. 11-centimeter lenses observing persistently from good sites can find planets around bright nearby stars, often the best targets for detailed characterization because brighter stars provide more photons for spectroscopic analysis. By 2010, when HAT P26b was discovered, HATNet had already found dozens of transiting planets and established itself as one of the leading ground-based planet discovery programs. The project continues operating today, searching for planets and refining techniques that have inspired similar surveys worldwide. Chapter 3. Characteristics of HAT P26b. Let's examine HAT P26b's characteristics in detail, because they place it in the warm Neptune category, a fascinating class of planets intermediate between super-Earths and gas giants. HAT P26b is classified as a warm Neptune or sub-Saturn, planets with Neptune-like sizes, but orbiting close enough to their stars to be significantly hotter than our solar system's ice giants. At 0.557 Jupiter radii, or about 6 Earth radii, HAT P26b is almost exactly Neptune's size. Neptune has a radius of about 3.8 Earth radii at its equator, while Uranus is about 4 Earth radii. So HAT P26b is somewhat larger, but in the same general class. The physical characteristics are well determined from transit and radial velocity observations. The radius is 0.557 Jupiter radii, or about 6.21 Earth radii. The mass is 0.059 Jupiter masses, or about 18.8 Earth masses. The density is approximately 0.4 grams per cubic centimeter. This low density indicates HAT P26b is not rocky. It must be composed largely of light elements. The planet likely has a small rocky icy core, perhaps a few Earth masses, surrounded by a substantial hydrogen-helium envelope comprising most of the planet's mass. This structure is typical for Neptune-sized planets, which are too small to accumulate massive hydrogen envelopes like Jupiter, but large enough to retain significant primordial atmospheres. The surface gravity is approximately 0.54 times Earth's gravity, meaning objects on HAT P26b would weigh about half what they do on Earth. This relatively low gravity affects atmospheric properties. Lower gravity creates a larger atmospheric scale height, making atmospheric features more prominent in spectroscopic observations. The orbital characteristics place HAT P26b in the warm Neptune regime. The orbital period is 4.2346 days, about 102 hours. The semi-major axis is 0.0477 AU, approximately 7.1 million kilometers or 4.4 million miles. Mercury orbits the Sun at 0.39 AU. So HAT P26b orbits about 8 times closer to its star than Mercury does to ours. At this distance, the planet is certainly tidally locked with one hemisphere permanently facing the star. The orbital eccentricity is low, approximately 0.04, meaning the orbit is nearly circular, typical for close-in planets where tidal forces circularize orbits rapidly. The equilibrium temperature is estimated at approximately 900 Kelvin, or about 627 degrees Celsius, or 1,160 degrees Fahrenheit. This is hot. Water would be steam, but not as extreme as hot Jupiter's exceeding 1,500 Kelvin. The warm designation distinguishes it from hot Jupiter's at higher temperatures. At 900 Kelvin, atmospheric chemistry is complex. Water exists as vapor. Methane might be present, but is unstable at these temperatures. Carbon monoxide becomes important. Atmospheric dynamics are vigorous with supersonic winds likely transporting heat from day side to night side. The host star HAT P26 is a K1 dwarf star, slightly smaller and cooler than our Sun. The stellar mass is approximately 0.82 solar masses. The radius is 0.79 solar radii. The temperature is approximately 5,079 Kelvin, cooler than the Sun's 5,778 Kelvin. The age is estimated at several billion years, indicating a mature main sequence star. The metallicity is approximately solar, meaning similar abundances of elements heavier than hydrogen and helium. The distance from Earth is approximately 437 light-years, moderately distant, but close enough that detailed observations are feasible with large telescopes and space observatories. Chapter 4. The Clear Atmosphere Discovery. What transformed HAT P26b from a moderately interesting warm Neptune into a scientifically crucial target was the discovery of its remarkably clear atmosphere. In 2016, a team of astronomers used the Hubble Space Telescope to observe HAT P26b's atmosphere through transmission spectroscopy. This technique observes the planet's transit at multiple wavelengths, looking for atmospheric absorption features revealing composition. When starlight passes through the planet's atmosphere during transit, different molecules absorb light at characteristic wavelengths. By measuring how much light is blocked at each wavelength, astronomers can identify which molecules are present and in what abundances. For most Neptune-sized exoplanets studied previously, transmission spectra were disappointingly flat, showing little wavelength variation. Flat spectra typically indicate high-altitude clouds or hazes blocking the view of deeper atmospheric layers where molecular absorption occurs. This atmospheric opacity made it difficult to determine composition or understand atmospheric chemistry for most planets in this size range. But when the team analyzed HAT P26b's transmission spectrum, they found something remarkable: strong, clear water vapor absorption features spanning multiple wavelengths. The spectrum wasn't flat. It showed pronounced variations indicating a relatively clear, transparent atmosphere, allowing observation of deep atmospheric layers. The water vapor detection was definitive, with features visible across optical and near-infrared wavelengths. The strength of these features indicated substantial water abundance and, crucially, relatively little obscuration by high-altitude clouds. This made HAT P26b one of the clearest Neptune-sized planet atmospheres ever observed. Follow-up observations using Spitzer Space Telescope at longer infrared wavelengths confirmed and extended these findings, detecting additional molecular features and further constraining atmospheric properties. The results were published in 2017 in a paper in Science magazine, highlighting the exceptional clarity of HAT P26b's atmosphere and its value as a benchmark for understanding Neptune-sized planets. Why is HAT P26b's atmosphere so clear when similar planets are cloudy? Several factors might contribute. The relatively low atmospheric metallicity, about 5 times solar rather than the 100 times solar metallicity inferred for some other Neptunes, might inhibit cloud condensate formation. The temperature of 900 Kelvin might be in a sweet spot where common cloud materials don't condense efficiently. Or atmospheric dynamics might prevent cloud particles from reaching high altitudes. The exact reasons remain uncertain, but the result is clear. HAT P26b provides an unprecedented window into Neptune-sized planet atmospheric chemistry unobscured by clouds. The atmospheric metallicity measurement itself was scientifically important. By comparing the observed water abundance to stellar values and using atmospheric models, the team inferred HAT P26b's atmospheric metallicity is about 4.8 times solar, significantly enriched in heavy elements compared to the host star, but lower than Jupiter's atmospheric metallicity and much lower than some other Neptunes. This metallicity provides clues about formation. Planets that accrete more solids, ices and rocks, during formation have higher atmospheric metallicities. HAT P26b's moderate enrichment suggests it formed from a mix of gas and solids, consistent with formation beyond the snow line followed by inward migration. The clear atmosphere discovery transformed HAT P26b into one of the most valuable Neptune-sized planets for testing atmospheric models, understanding cloud formation physics, and revealing the chemical composition of planets in this mass range. Chapter 5: Atmospheric Composition. What have atmospheric observations revealed about HAT P26b's composition and chemistry? The transmission spectrum observations definitively detected water vapor at multiple wavelengths, confirming H2O is abundant in HAT P26b's atmosphere, as expected for a hydrogen-rich planet with oxygen-bearing molecules. Water is one of the most important molecules in planetary atmospheres and one of the most sought-after detections. The water features span from optical to infrared wavelengths, appearing in data from both Hubble and Spitzer telescopes. The consistent detection across multiple instruments and wavelength ranges provides confidence in the result and allows detailed abundance estimates. Based on the strength of water absorption features and atmospheric modeling, scientists estimate water vapor comprises a significant fraction of the molecules in the observable atmospheric layers, with abundance roughly consistent with solar elemental ratios accounting for atmospheric temperature and pressure effects. In addition to water, atmospheric models and observations suggest the presence of carbon monoxide, which forms at high temperatures when oxygen and carbon combine. The carbon monoxide to methane ratio depends on temperature and atmospheric chemistry, with carbon monoxide favored at HAT P26b's 900 Kelvin temperature. Sodium and potassium, alkali metals that create strong optical absorption features, have been searched for but not definitively detected, possibly because they're depleted into cloud particles or exist in regions of the atmosphere not accessible to current observations. The atmospheric metallicity measurement, about 5 times solar, is one of the most precise metallicity estimates for any Neptune-sized exoplanet. This measurement comes from comparing observed abundances to stellar values and using theoretical models of atmospheric chemistry and cloud formation. This moderate metallicity places HAT P26b intermediate between Jupiter, whose atmosphere is enriched 3 to 5 times solar, and some other Neptunes inferred to have metallicities exceeding 100 times solar. The variation in atmospheric metallicity across planets reveals diversity in formation conditions and solid accretion efficiency. Temperature structure is another key atmospheric property revealed by observations. The relatively clear atmosphere allows probing multiple atmospheric layers at different pressures and temperatures. Models suggest temperature increases from about 600 Kelvin in upper layers to over 1,000 Kelvin deeper in the atmosphere, with possible temperature inversions where certain layers are hotter than layers above or below. Atmospheric circulation models predict vigorous dynamics driven by day-night temperature contrasts. Supersonic winds likely race around the planet at several kilometers per second, transporting heat from the permanent day side to the night side. These winds affect observable atmospheric properties, influencing where the hottest regions are located and how efficiently heat redistribution occurs. The clear atmosphere provides a rare opportunity to test these circulation models against observations, though detecting atmospheric dynamics directly requires observations challenging with current technology. Chapter 6. Scientific significance. Why does HAT P26b matter for exoplanet science? HAT P26b's significance extends across several research areas. First, atmospheric benchmark. As one of the clearest Neptune-sized planet atmospheres observed, HAT P26b serves as a crucial benchmark for understanding atmospheric composition, chemistry, and physics for planets in this mass range. Atmospheric models tested against HAT P26b's data can then be applied to cloudier planets where direct observations are more limited. Second, cloud formation physics. Why is HAT P26b's atmosphere clear when similar planets are cloudy? Understanding this reveals the processes controlling cloud formation, atmospheric opacity, and observability. The factors making HAT P26b's atmosphere transparent might be metallicity, temperature, atmospheric dynamics, or other variables. Identifying which matters helps predict which planets will have clear versus cloudy atmospheres. Third, formation and migration insights. The atmospheric metallicity measurement provides clues about formation conditions. HAT P26b's moderate 5 times solar metallicity suggests it accreted significant solids, but not the enormous solid budgets inferred for some ultrametal-rich Neptunes. This constrains formation location and migration timescales. Fourth, population context. HAT P26b represents one example in the diverse population of Neptune-sized exoplanets. By characterizing many such planets and comparing their properties, astronomers identify patterns revealing formation and evolution processes. HAT P26b, with its clear atmosphere and well-measured properties, is a crucial data point for population studies. Fifth, observational technique development. The successful atmospheric characterization of HAT P26b demonstrates what's possible with Hubble and Spitzer for bright nearby targets. guiding target selection and observing strategies for JWST and future missions. These contributions make HAT P26b valuable not just as an interesting individual planet, but as a crucial reference point for understanding the entire population of Neptune-sized exoplanets, one of the most common planet types in the galaxy. Chapter 7. Comparative Context. How does HAT P26b compare to other Neptune-sized planets? And what does this reveal? HAT P26b sits in a population of warm and hot Neptunes with diverse atmospheric properties. Some, like GJ436b, show evidence for atmospheric escape and possible methane clouds. Others, like HAT P11b, have cloudy atmospheres with muted spectral features. And still others, like GJ3470b, are losing atmospheres through photoevaporation. What distinguishes HAT P26b is its atmospheric clarity. The strong water features and relatively cloud-free spectrum make it exceptional for its size class. This clarity enables atmospheric characterization impossible for cloudier planets, revealing composition and chemistry in unprecedented detail. The diversity of atmospheric properties across Neptune-sized planets, from ultra-cloudy to remarkably clear like HAT P26b, reveals that Neptune-sized planets don't have uniform atmospheres. Instead, factors like metallicity, temperature, host star properties, and formation history create enormous variety in atmospheric observability and composition. Understanding what makes some atmospheres clear and others cloudy is crucial for predicting which planets will be best targets for future atmospheric characterization and for understanding the physical processes controlling atmospheric properties. Chapter 8. Future Research. What's next for studying HAT P26b? The James Webb Space Telescope is observing or will observe HAT P26b as one of the best Neptune-sized targets for atmospheric characterization. JWST's extended wavelength coverage, higher sensitivity, and multiple specialized instruments enable detections impossible with Hubble or Spitzer. For HAT P26b, JWST can detect additional molecules like carbon dioxide, methane, and others, measure abundances more precisely, constrain atmospheric temperature structure and dynamics, search for photochemical products and disequilibrium chemistry, and potentially detect trace species revealing formation conditions. Ground-based high-resolution spectroscopy might enable detection of carbon monoxide, water, and other molecules through their individual absorption lines, complementing space-based observations with different techniques probing different atmospheric regions. Long-term monitoring might detect atmospheric variability indicating weather, cloud changes, or other temporal phenomena, though detecting such variations requires repeated observations over months or years. Comparative studies observing many Neptune-sized planets will identify which factors most strongly influence atmospheric properties, building statistical understanding that individual observations can't provide. Chapter 9. Conclusion. Let's recap what makes HAT P26b scientifically important. HAT P26b is a warm Neptune discovered in 2010 by HATNet with 0.557 Jupiter radii, 0.059 Jupiter masses, and a density of 0.4 grams per cubic centimeter orbiting every 4.2 days at 0.048 AU. With temperatures around 900 Kelvin, it's hot but not extreme. What makes it exceptional is its remarkably clear atmosphere revealed by Hubble observations in 2016 to 2017. Unlike most Neptune-sized planets showing flat, cloudy spectra, HAT P26b's transmission spectrum shows strong water vapor features indicating an unusually transparent atmosphere, allowing unprecedented views into its composition and chemistry. This clarity has made HAT P26b one of the most valuable Neptune-sized planets for atmospheric science, serving as a benchmark for understanding planets in this mass range and revealing the surprising diversity of atmospheric properties across the exoplanet population. 437 light-years away. HAT P26b continues its rapid orbit, completing more than 86 circuits per Earth year. One hemisphere faces a sun-like star, heated to 900 Kelvin. The other knows only darkness, cooled by supersonic winds. And throughout its atmosphere, molecules reveal themselves to our telescopes. Water vapor absorbing infrared light, creating the spectral signatures that transform this distant world from a point of light into a laboratory for understanding planetary atmospheres. HAT P26b reminds us that nature creates surprises. When astronomers expected clouds obscuring atmospheric signals, this planet offered clarity. When we thought Neptune-sized planets would all look similar, this one showed us diversity. The story of HAT P26b teaches us that sometimes the most valuable discoveries come not from finding the most extreme planets, but from finding planets whose properties, in this case, atmospheric clarity, make them ideal laboratories for testing our understanding. Every planet with a clear atmosphere is precious because it offers windows into planetary interiors and formation that cloudy planets can't provide. HAT P26b, with one of the clearest Neptune-sized planet atmospheres known, will remain a crucial reference point for understanding this planet class for years to come. I hope you're ready for this next one, because things are about to get weird. With GJ 3512b, the planet that shouldn't exist. In 2019, astronomers announced a discovery that should have been impossible. Around a tiny red dwarf star 1/8 the Sun's mass, they found a gas giant planet with nearly half Jupiter's mass. The planet-to-star mass ratio was so extreme, 1 to 260, that it violated every expectation of how planets form around small stars. According to core accretion theory, the dominant model explaining how planets form, there simply wasn't enough material in the protoplanetary disk around such a small star to build a planet this massive. And yet, there it was, GJ 3512b, orbiting every 204 days, challenging decades of theoretical work and forcing astronomers to reconsider fundamental assumptions about planetary formation. This is the story of the planet that shouldn't exist, and what it teaches us about how nature builds worlds in ways we didn't expect. A massive gas giant discovered in 2019 that immediately became one of the most scientifically important exoplanets. Not because it might be habitable, not because it's the largest or hottest, but because its mere existence challenged our understanding of how planets form. Before we dive in, I need to clarify something important. Despite being listed as a super-Earth in some databases or prompts, GJ 3512b is definitely not a super-Earth. It's a gas giant with a minimum mass of approximately 0.46 Jupiter masses, about 146 Earth masses. That's roughly the mass of Saturn. This is a massive planet, not a rocky super-Earth. What makes GJ 3512b extraordinary is not its absolute mass, but its mass relative to its host star. GJ 3512 is an M5.5 dwarf, a very small, cool red dwarf with only 0.12 solar masses, or about 123 Jupiter masses. The planet has approximately 0.37% of the star's mass, creating a planet-to-star mass ratio of about 1 to 260. To put this in perspective, Jupiter has about 0.1% of the Sun's mass, a ratio of 1 to 1,000. GJ 3512b is roughly 4 times more massive relative to its star than Jupiter is to the Sun. This extreme mass ratio is unprecedented for a planet around such a low-mass star and immediately raised red flags about formation mechanisms. According to core accretion theory, the standard model for planet formation where solid cores grow large enough to gravitationally capture gas envelopes. There shouldn't have been enough solid material in GJ 3512's protoplanetary disk to build such a massive planet. The discovery forced serious consideration of an alternative formation mechanism, gravitational instability, where regions of the gas disk collapse directly into planets without needing to build solid cores first. Discovered through patient radial velocity monitoring by the Carmenes spectrograph and published in Science magazine in September 2019, GJ3512b represents a paradigm-shifting discovery that continues influencing how we think about planetary formation, especially around M-dwarf stars. Today we're going to explore how GJ3512b was discovered through precision radial velocity measurements, what its extreme characteristics tell us about the limits of planet formation, why core accretion theory struggles to explain this planet, how gravitational instability might create massive planets around small stars, what this discovery means for understanding planetary systems around M-dwarfs, and what future observations might reveal about this remarkable system. Let's discover the planet that rewrote the rules. Chapter 1. The Carmenes Survey. GJ3512b was discovered by Carmenes, a precision spectrograph specifically designed to search for planets around M-dwarf stars. Carmenes stands for Kähler Alto High Resolution Search for M-dwarfs with exo-Earths with near-infrared and optical Echelle spectrographs. Quite a mouthful, but it describes exactly what this instrument does. Carmenes is installed at the 3.5-meter telescope at Kähler Alto Observatory in Spain and has been operating since 2016. The instrument is optimized for M-dwarf observations, using both optical and near-infrared channels to measure stellar spectra with extreme precision. M-dwarfs emit most of their light in the red and infrared parts of the spectrum, so having an infrared channel is crucial for achieving the best measurements. Carmenes can measure stellar radial velocities, the speed at which stars move toward or away from us, with precision approaching 1 meter per second. This extraordinary precision enables detection of planets, inducing tiny gravitational wobbles in their host stars. The Carmenes survey targets nearby M-dwarfs, searching for planets through the radial velocity method. As a planet orbits, its gravity pulls the star slightly, causing the star to wobble. This wobble creates Doppler shifts in the star's spectral lines, shifting toward blue wavelengths when a star moves toward us and toward red when moving away. By measuring these Doppler shifts repeatedly over months and years, astronomers detect periodic velocity variations indicating planets. The amplitude of the velocity variation reveals the planet's minimum mass. The period of variation gives the orbital period, and the shape of the velocity curve reveals orbital eccentricity. Why focus specifically on M-dwarfs? Several reasons make them excellent targets for planet detection. First, M-dwarfs are small and low mass, so planets create proportionally larger wobbles, easier to detect. Second, M-dwarfs are the most common stars in the galaxy, accounting for about 70% of all stars. Understanding planets around M-dwarfs means understanding most planetary systems. Third, many M-dwarfs are nearby, allowing detailed characterization. The Carmenes survey has discovered dozens of planets and continues monitoring hundreds of nearby M-dwarfs. GJ3512b stands out as one of the survey's most scientifically significant discoveries. Not the first planet found, but arguably the most theoretically challenging. Chapter 2. The Discovery. Between 2016 and 2018, Carmenes monitored GJ3512, accumulating radial velocity measurements that revealed an unmistakable planetary signal. GJ3512 is a relatively nearby M-dwarf at about 9 parsecs or 30 light-years from Earth. As an M5.5 dwarf, it's small, about 0.136 solar radii, or roughly 1.5 times Jupiter's diameter. It's cool. Temperature around 3,000 Kelvin compared to the Sun's 5,778 Kelvin. And it's faint, magnitude 14.6, far too dim for naked eye observation, but accessible to telescopes. The Carmene's radial velocity data showed a clear periodic signal with an amplitude of approximately 122 meters per second repeating every 204 days. This was an enormous signal, much larger than the few meters per second wobble Jupiter induces in the Sun or the half-meter per second wobble Earth induces. From this radial velocity signal, astronomers could calculate the planet's minimum mass. The minimum mass came out to approximately 0.46 Jupiter masses, or about 146 Earth masses, roughly Saturn's mass. The minimum qualifier is important because radial velocity measurements can't determine orbital inclination, how tilted the orbit is relative to our line of sight. If the orbit is viewed edge-on, the minimum mass equals the true mass. If viewed at an angle, the true mass is higher. For most planetary systems, orbital inclinations are random, and statistical arguments suggest the true mass is typically within about 50% of the minimum mass. So GJ 3512b's true mass is probably between 0.46 and 0.7 Jupiter masses. Definitely a massive gas giant, not a super-Earth or mini-Neptune. The orbital period of 204 days places GJ 3512b at a semi-major axis of approximately 0.338 AU, about 50 million kilometers or 31 million miles from its star. For comparison, Mercury orbits the Sun at 0.39 AU, so GJ 3512b orbits slightly closer than Mercury's orbit. However, because GJ 3512 is a cool, dim M dwarf, the stellar flux received by GJ 3512b is much less than Mercury receives from the Sun. The planet is probably in or near the habitable zone. Though as a gas giant without a solid surface, habitability for the planet itself is not relevant. The orbital eccentricity is moderately high at approximately 0.436, meaning the orbit is noticeably elliptical. The orbital distance varies from about 0.19 AU at periastron to 0.485 AU at apastron, more than a twofold variation. This high eccentricity was another surprise and provides clues about the system's dynamical history. Additionally, the radial velocity data showed hints of a second planet, GJ 3512c, with a longer orbital period around 1,500 days and minimum mass around 0.17 Jupiter masses. While GJ 3512c requires confirmation from additional observations, its presence suggests this is a multi-planet system with complex dynamics. The discovery was announced in September 2019 in a paper published in Science magazine titled "A Giant Exoplanet Orbiting a Very Low Mass Star Challenges Planet Formation Models." The title captured the key point: this planet shouldn't exist according to standard formation theory. Chapter 3: Characteristics of GJ 3512b. Let's examine GJ 3512b's characteristics in detail, because they reveal why this planet is so challenging to explain. GJ 3512b is classified as a gas giant, a planet composed primarily of hydrogen and helium with possibly a rocky icy core. At a minimum mass of 0.46 Jupiter masses, it's roughly Saturn-sized, though without transit observations we can't measure its radius directly. Assuming a typical radius for a gas giant of this mass and temperature, GJ 3512b likely has a radius around 0.8 to 1.0 Jupiter radii. This would give a density roughly similar to Saturn's at 0.7 grams per cubic centimeter, low density consistent with a hydrogen-helium-dominated composition. The planet orbits its star every 203.59 days, with an orbital distance varying from 0.19 to 0.485 AU due to the high eccentricity of 0.436. At apastron, the planet receives stellar flux similar to Mars at the Sun. At periastron, it receives flux more like Venus. This variation affects atmospheric temperature and dynamics significantly. The equilibrium temperature likely ranges from about 250 to 400 Kelvin, depending on orbital position. Cool by hot Jupiter standards, but warmer than Jupiter's 165 Kelvin. At these temperatures, water ice, methane ice, and ammonia ice could condense in the upper atmosphere, depending on composition and pressure. The host star GJ3512 is an M5.5 dwarf with approximately 0.12 solar masses, about 1/8 the Sun's mass, or 123 Jupiter masses. The radius is 0.136 solar radii, making it only slightly larger than Jupiter. The temperature is approximately 3,000 Kelvin, and the age is estimated at several billion years. The critical parameter is the planet-to-star mass ratio, with the planet at 0.46 Jupiter masses minimum and the star at 123 Jupiter masses. The ratio is approximately 1 to 267, or 0.374%. This is extraordinarily high compared to most planetary systems. For context, Jupiter is 0.1% of the Sun's mass. Saturn is 0.03%. Even massive hot Jupiters around Sun-like stars rarely exceed 0.3%. GJ3512b exceeds all of these, creating an extreme mass ratio that standard planet formation theory struggles to explain. The high orbital eccentricity of 0.436 is also unusual for planets at this orbital distance. Typical planets at similar distances have low eccentricities, circularized by tidal forces over millions of years. The preservation of high eccentricity suggests either the planet is young and hasn't had time to circularize, or something is pumping the eccentricity, possibly gravitational interactions with the suspected second planet GJ3512c. Chapter 4. The Formation Problem. Why does GJ3512b's existence challenge planetary formation theory? Let's understand the problem. Planets form in protoplanetary disks, rotating disks of gas and dust surrounding young stars. For decades, the dominant formation model has been core accretion, which successfully explains most planets in our solar system and many exoplanets. Core accretion works like this. Solid particles, dust, ice, rock, stick together through collisions, growing from microscopic grains to pebbles to boulders to planetesimals kilometers across. These planetesimals continue colliding and merging, eventually forming planetary cores. Once a core reaches about 10 Earth masses, its gravity becomes strong enough to rapidly capture surrounding hydrogen and helium gas, forming a gas giant. This model works well for explaining Jupiter and Saturn. Jupiter's core is estimated at 10 to 30 Earth masses, with the remaining 300 or so Earth masses being captured gas. The process requires enough solid material to build the core and enough time to capture gas before the protoplanetary disk dissipates in a few million years. Here's the problem for GJ3512b. The amount of solid material available in a protoplanetary disk depends on the star's mass. More massive stars have more massive disks with more solids. Low-mass M dwarfs have low-mass disks with correspondingly little solid material. For GJ3512 with only 0.12 solar masses, theoretical models predict the protoplanetary disk contained very little solid material, probably not enough to build a 10 Earth mass core necessary to trigger runaway gas accretion. The disk simply didn't have sufficient raw materials to make a Saturn mass planet via core accretion. Multiple research teams ran simulations of planet formation around 0.12 solar mass stars using core accretion models. The results consistently showed that such stars can form rocky planets and mini-Neptunes, but struggle to form gas giants. The maximum planet mass formed in simulations was typically well below GJ3512b's observed mass. Yet GJ3512b exists. This presents a fundamental challenge. Either our understanding of protoplanetary disk masses around M-dwarfs is wrong, or GJ3512b formed through a different mechanism than core accretion. Intergravitational instability, an alternative planet formation mechanism where regions of the gas disk become so dense they collapse directly into planets without needing to first build solid cores. This process is like star formation, but on planetary mass scales. Gravitational instability can work if the disk is massive enough and cool enough that self-gravity overcomes pressure support. When conditions are right, spiral density waves form in the disk, and overdense regions fragment into bound objects. Protoplanets composed primarily of hydrogen and helium from start. Gravitational instability can potentially form massive planets quickly, within thousands of years rather than millions, and doesn't require building a solid core first. This makes it viable for producing massive planets, even in lower mass disks where core accretion fails. The catch is that gravitational instability requires specific conditions: a disk massive enough relative to the star, cool temperatures to reduce pressure support, and sufficient angular momentum. These conditions are most easily met at large orbital distances, several AU or more, rather than close-in, where GJ3512b orbits at 0.34 AU. However, if GJ3512b formed at several AU via gravitational instability and then migrated inward through disk interactions or dynamical scattering, this could explain its current location while avoiding the core accretion problem. The high orbital eccentricity supports this scenario. Planets formed via gravitational instability often have eccentric orbits because the instability process creates asymmetries. Additionally, if GJ3512c exists and had close gravitational encounters with GJ3512b, this could have excited the eccentricity while causing one or both planets to migrate. Chapter 5: Implications for Planet Formation. What does GJ3512b teach us about how planets form? GJ3512b's discovery has several profound implications for planetary formation theory. First, it demonstrates that massive planets can form around very low-mass stars, despite theoretical predictions suggesting this should be rare or impossible via core accretion. This means our models of either disk masses, core accretion efficiency, or both need revision for M-dwarf systems. Second, it provides strong evidence that gravitational instability is a viable planet formation mechanism, at least under certain conditions. While gravitational instability has been theoretically explored for decades, clear observational evidence for planets formed this way has been elusive. GJ3512b is a strong candidate. Third, it reveals that planet-to-star mass ratios can be much more extreme than previously thought possible. If nature can produce ratios of 1 to 260, this expands the parameter space of possible planetary systems dramatically. Fourth, it suggests that planetary system architectures around M-dwarfs might be more diverse than anticipated. If gravitational instability operates around M-dwarfs, we should expect to find more massive planets at wide separations where this formation mechanism is efficient. Fifth, the high eccentricity and possible second planet indicate complex dynamical histories. Planet-planet scattering or secular perturbations might be common in systems formed via gravitational instability, potentially leading to ejections, collisions, or highly eccentric orbits. The discovery also impacts expectations for habitable planets around M-dwarfs. If massive gas giants form around these stars, they might disrupt interplanetary systems where habitable terrestrial planets could exist. Alternatively, if massive planets migrate inward, they might clear out material that would otherwise form terrestrial planets. Or they might migrate, then stop, leaving inner regions available for terrestrial planet formation later. Understanding these processes matters because M-dwarfs host most of the galaxy's potentially habitable real estate. If we want to assess the frequency of habitable planets galaxy-wide, we need to understand how planetary systems form and evolve around M dwarfs, including the role of massive outer planets like GJ 3512b. The discovery also highlights the importance of radial velocity surveys targeting M dwarfs. While transit surveys like TESS and Kepler discover thousands of planets, they're biased toward finding close-in planets with short periods. Radial velocity surveys can detect longer-period planets at wider separations where gravitational instability operates, exactly the parameter space crucial for understanding formation mechanisms. Chapter 6, Comparative Context. How does GJ 3512b compare to other exoplanets, and what makes it unique? GJ 3512b stands out primarily for its extreme planet-to-star mass ratio. While many massive planets are known around Sun-like stars, and many planets are known around M dwarfs, if you combine both characteristics, a massive planet around a very low-mass star. A few other systems have high planet-to-star mass ratios, but GJ 3512b is among the most extreme. The discovery demonstrated that this parameter space exists and is accessible to observations, prompting searches for similar systems. Compared to typical M-dwarf planets discovered by transit surveys, which tend to be super-Earths and mini-Neptunes at very short periods, GJ 3512b is much more massive and at a much wider separation. This reveals that M-dwarf planetary systems have more architectural diversity than early transit surveys suggested. The high eccentricity is also somewhat unusual. Many exoplanets have low eccentricities, especially close-in planets circularized by tides. GJ 3512b's orbit has remained eccentric despite being old enough for circularization, suggesting recent dynamical disruption or ongoing perturbations from the suspected second planet. The combination of high mass, high eccentricity, long period, and low-mass host star makes GJ 3512b essentially unique in the exoplanet catalog. Not because each individual characteristic is unprecedented, but because the combination challenges formation models so directly. Chapter 7, Future Research. What's next for studying GJ 3512b and systems like it? Several research directions could advance our understanding. Continued radial velocity monitoring could confirm the suspected second planet GJ 3512c and measure its properties precisely. If GJ 3512c exists, studying the dynamical interactions between the two planets would reveal their formation and migration history. Direct imaging might eventually resolve GJ 3512b if it's massive and young enough to be self-luminous from formation heat. While challenging, next-generation extremely large telescopes with advanced adaptive optics might achieve this. Searching for similar systems, massive planets around very low-mass stars, would reveal whether GJ 3512b is truly unusual or just the first of many such systems. If common, this would strongly support gravitational instability as a standard formation pathway. If rare, it suggests GJ 3512b formed under special circumstances. Theoretical modeling continues refining predictions for what conditions enable gravitational instability and how frequently this creates massive planets around M dwarfs. Comparing model predictions to observational statistics tests our understanding. Long-term astrometric measurements from missions like Gaia might detect the stellar wobble induced by GJ 3512b through position measurements, providing an independent mass measurement and constraining orbital inclination to determine true mass versus minimum mass. Chapter 8, Conclusion. Let's recap why GJ 3512b is one of the most scientifically important exoplanets discovered in recent years. GJ 3512b is a gas giant with minimum mass 0.46 Jupiter masses orbiting every 204 days at 0.34 AU from an M5.5 dwarf star with only 0.12 solar masses. The planet-to-star mass ratio of 1 to 267 is so extreme that core accretion theory, the standard planet formation model, struggles to explain how this planet formed. The discovery, announced in 2019 from CARMEN's radial velocity observations, immediately challenged theoretical expectations and forced serious consideration of gravitational instability, where gas disks collapse directly into planets, as an alternative formation mechanism. With high orbital eccentricity and evidence for a second massive planet, the GJ3512 system exhibits complex dynamics that provide clues about formation and migration. The system reveals that planetary architecture around M dwarfs is more diverse than early observations suggested, and that massive planets can form even around very low-mass stars. 30 light-years away, GJ3512b continues its eccentric 204-day orbit around a star 1/8 the Sun's mass. As the planet swings from 0.19 to 0.485 AU, temperatures vary from Mars-like to Venus-like conditions. Hydrogen and helium dominate this world, possibly surrounding a rocky icy core. This planet shouldn't exist, at least not according to decades of planet formation theory. Its mere presence forced astronomers to question fundamental assumptions, consider alternative formation mechanisms, and recognize that nature creates planetary systems in ways we're still learning to understand. GJ3512b reminds us that the universe doesn't follow our rules. Theories are human constructions attempting to describe reality. And when reality contradicts theory, reality always wins. Our job is to revise the theories until they match what nature actually produces. The story of GJ3512b exemplifies how astronomy advances. A single unexpected discovery can reveal gaps in our understanding, prompt theoretical work explaining the observations, and ultimately lead to better models that explain not just the new discovery, but many other phenomena. Before GJ3512b, most astronomers thought massive gas giants couldn't form around very low-mass M dwarfs. Now we know they can, and we're working to understand how. This discovery opened eyes to gravitational instability as a potentially common formation mechanism and expanded our conception of what planetary systems can look like. Every paradigm-shifting discovery, from 51 Pegasi b revealing hot Jupiters exist, to GJ3512b showing massive planets orbit tiny stars, teaches us humility about our theories and excitement about what else we haven't yet imagined. Next, let's warp on over to WASP 118b, a hot Jupiter from the WASP survey. 680 light-years from Earth, a gas giant slightly larger than Jupiter orbits its star every 4 days. Heated to over 1500 Kelvin by its nearby sun, WASP 118b represents one of hundreds of hot Jupiters discovered by ground-based telescopes systematically surveying the sky for transiting planets. This is WASP 118b, a world discovered in 2014 through persistent observation, confirmed through follow-up measurements, and studied to understand how gas giants behave under extreme stellar heating. It's a testament to how ground-based surveys continue finding planets that expand our understanding of planetary diversity across the galaxy. A hot Jupiter discovered in 2014 by the Wide-Angle Search for Planets project that exemplifies the continued success of ground-based exoplanet surveys in finding transiting planets around bright stars accessible for detailed study. The discovery of exoplanets has created an enormous catalog of worlds, each contributing to our statistical understanding of planetary populations, testing our formation and evolution theories, and revealing the incredible diversity of planetary systems filling our galaxy. WASP 118b might not make headlines like the most extreme discoveries, the hottest planets, the most inflated, or those in habitable zones. But it represents something equally important, a well-characterized hot Jupiter that helps define what these planets are typically like across the galaxy. By studying many hot Jupiters like WASP, 118b, planets with moderate properties, typical orbits, representative characteristics, we build the comprehensive picture needed to understand gas giant physics and planetary system architecture. Discovered through the transit method by the WASP South facility in South Africa and confirmed through radial velocity follow-up observations. WASP 118b orbits a relatively bright star, making it accessible for atmospheric characterization and detailed study. It joins over 200 WASP discoveries that have transformed our understanding of how planetary systems form and evolve. Today we're going to explore how the WASP project operates and why it's been so successful at finding transiting planets, how WASP 118b was discovered and confirmed as a genuine planet, what its physical characteristics tell us about hot Jupiter properties, what we've learned or might learn about its atmosphere, why studying representative hot Jupiters advances planetary science, and what future observations might reveal about this distant world. Let's discover what ground-based surveys continue teaching us about planetary diversity. Chapter 1. The WASP Project. WASP 118b was discovered by the Wide-Angle Search for Planets, one of the most successful ground-based exoplanet surveys operating over the past 2 decades. The WASP project, which we've explored in previous videos, began operations in 2004 with a straightforward but powerful concept. Use arrays of small, wide-field cameras to monitor hundreds of thousands of bright stars simultaneously, searching for the periodic dimming that indicates transiting planets. WASP operates from 2 sites providing complete sky coverage. Super WASP North, located at La Palma in the Canary Islands, monitors Northern Hemisphere stars. Super WASP South, operating from the South African Astronomical Observatory, covers Southern Hemisphere stars. Together, these facilities have surveyed essentially the entire sky visible from Earth, monitoring over 1 million stars and discovering over 200 confirmed exoplanets. Each WASP facility consists of 8 wide-field cameras using 200mm camera lenses, essentially high-quality telephoto lenses similar to what professional photographers use. Each camera covers approximately 64 square degrees of sky, and together the 8 cameras at each site monitor hundreds of square degrees simultaneously. The observing strategy is systematic and persistent. Throughout each clear night, the WASP cameras photograph their target fields repeatedly, building up light curves, plots of brightness versus time, for every star in the field. These observations continue night after night, season after season, accumulating years of data on hundreds of thousands of stars. Automated pipelines analyze these light curves, searching for periodic dimming that could indicate transiting planets. When a promising signal appears, it's flagged for follow-up observations. WASP itself can detect the transit signal and measure the planet's size and orbital period, but confirming the planet and determining its mass requires additional observations from other telescopes. The follow-up process involves several steps. High-resolution imaging from larger telescopes verifies the target is a single star without close companions that could create false signals. Spectroscopy characterizes the host star's properties, its temperature, mass, composition, and evolutionary state. And radial velocity measurements detect the gravitational wobble induced by the planet's mass, confirming it's a genuine planet rather than a false positive, like an eclipsing binary star. By 2014, when WASP 118b was discovered, the WASP project had already found over 100 exoplanets and was well established as one of the leading planet discovery programs worldwide. The project has been particularly successful at discovering hot Jupiters, large gas giants in very close orbits, because these planets create the largest transit signals and are easiest to detect with WASP's photometric precision. WASP's focus on relatively bright stars is strategically important. While space missions like Kepler and TESS can detect smaller planets around fainter stars, ground-based projects like WASP excel at finding planets around bright stars. Exactly the targets best suited for detailed atmospheric characterization and follow-up studies with spectroscopy. Chapter 2. The Discovery. Between approximately 2006 and 2013, WASP South accumulated observations of a star later designated WASP 118, detecting periodic transit signals indicating a Jupiter-sized planet. The automated analysis pipeline detected periodic transit signals occurring every 4.05 days. The dimming was approximately 1.3%. A substantial signal indicating a planet roughly Jupiter-sized, transiting a Sun-like star. The transit duration was about 2.7 hours, consistent with a close orbit around a main sequence star. And the transit shape matched expectations for a planetary transit rather than other phenomena that can mimic transits. From these transit observations, astronomers could immediately estimate several properties. The planet's radius, determined from how much light was blocked, was approximately 1.13 Jupiter radii, about 13% larger than Jupiter. The orbital period of 4.05 days indicated an extremely close orbit, and the transit timing precision suggested the orbit was likely circular, as tidal forces rapidly circularize orbits at such short distances. However, detecting a transit signal alone doesn't confirm a planet. Various false positive scenarios can mimic planetary transits, including eclipsing binary stars, hierarchical triple star systems, or background eclipsing binaries blended with the target star's light. Ruling out these alternatives requires comprehensive follow-up observations. For WASP 118b, confirming the planet required several types of follow-up observations conducted by research teams. High-resolution imaging from large ground-based telescopes verified that WASP 118 is a single star without close companions that could create false signals. These observations can detect companion stars separated by less than 1 arcsecond, closer than WASP's cameras could resolve. Spectroscopic observations from precision spectrographs characterized the host star in detail. By analyzing the star's spectrum, the rainbow of light broken into individual wavelengths, astronomers measured its temperature at approximately 6,100 Kelvin, its surface gravity indicating it's a main sequence star, and its metallicity showing enhanced abundances of heavy elements compared to the Sun. Radial velocity measurements from precision spectrographs detected the gravitational wobble induced by the planet's mass. As WASP 118b orbits, its gravity pulls the star slightly, causing the star to move toward and away from us. This motion creates a Doppler shift in the star's spectral lines, shifting toward blue wavelengths when moving toward us and toward red when moving away. The radial velocity measurements measured WASP 118b's mass at approximately 0.514 Jupiter masses, about 51% of Jupiter's mass, combined with the radius of 1.13 Jupiter radii from transits. This gives a density of approximately 0.36 grams per cubic centimeter, significantly less dense than Jupiter's 1.33 grams per cubic centimeter, indicating moderate inflation from stellar heating. WASP 118b was announced in 2014 in a paper published in a major astronomy journal, joining the catalog of WASP discoveries. The planet's properties, moderately inflated hot Jupiter orbiting a bright star, made it scientifically interesting and accessible for future atmospheric studies. Chapter 3. Characteristics of WASP 118b. Let's examine WASP 118b's characteristics in detail, because they place it comfortably within the hot Jupiter population. WASP 118b is classified as a moderately inflated hot Jupiter, a gas giant in a very close orbit with moderate radius expansion from stellar heating. The physical characteristics are well determined from combined transit and radial velocity observations. The radius is 1.13 Jupiter radii, making it approximately 13% larger in diameter than Jupiter. The mass is 0.514 Jupiter masses, about 51% of Jupiter's mass, roughly half. The density is 0.36 grams per cubic centimeter, indicating the planet is significantly less dense than Jupiter at 1.33 grams per cubic centimeter. This moderate inflation is typical for hot Jupiters at this temperature in stellar flux. The planet is expanded beyond what you'd expect for a cold Jupiter of this mass, but it's not extremely puffy like some hot Jupiters with densities below 0.2 grams per cubic centimeter. The inflation represents the balance between gravitational forces trying to compress the planet and stellar heating, preventing full contraction. The surface gravity is approximately 0.4 times Jupiter's gravity, less than half. This relatively low gravity compared to Jupiter affects atmospheric properties. Lower gravity creates a larger atmospheric scale height, which influences how prominent atmospheric features appear in spectroscopic observations. Inside WASP 118b, theoretical models predict a structure typical of hot Jupiters. A rocky or icy core, perhaps 10 to 20 Earth masses, surrounded by layers of metallic hydrogen under extreme pressure, molecular hydrogen in the middle regions, and an extended hot atmosphere heated by the nearby star. The moderate inflation suggests stellar heating is preventing gravitational contraction, but not causing extreme radius expansion that would require additional heating mechanisms. The orbital characteristics place WASP 118b firmly in the hot Jupiter category. The orbital period is 4.046 days, about 97 hours. The semi-major axis, average orbital distance, is approximately 0.051 AU, which is about 7.6 million kilometers or 4.7 million miles. Mercury orbits the Sun at 0.39 AU. WASP 118b orbits about 7.6 times closer to its star than Mercury does to ours. At this distance, WASP 118b is certainly tidally locked, with one hemisphere permanently facing the star and the other in perpetual darkness. The orbital velocity is approximately 140 kilometers per second. The orbital eccentricity is very low, essentially zero, meaning the orbit is circular. This is typical and expected for planets in such close orbits, as tidal forces rapidly circularize initially eccentric orbits within millions of years. The equilibrium temperature, the temperature the planet would have without considering atmospheric effects, is estimated at approximately 1500 to 1600 Kelvin, or about 1200 to 1300 degrees Celsius. This places WASP 118b in the moderately hot range for hot Jupiters, significantly hotter than any solar system planet, but not as extreme as ultra-hot Jupiters exceeding 2500 Kelvin. At these temperatures, atmospheric dynamics are vigorous. Supersonic winds likely race around the planet at several kilometers per second, transporting heat from the permanent day side to the night side. Despite this heat redistribution, the day-night temperature difference probably exceeds several hundred Kelvin. The host star, WASP 118, is an F6 star, slightly hotter and more massive than our Sun. The stellar mass is approximately 1.3 solar masses. The radius is about 1.32 solar radii, making it about 32% larger than the Sun. The temperature is approximately 6,100 Kelvin, compared to the Sun's 5,778 Kelvin. The age is estimated at several billion years, indicating a mature main sequence star. The metallicity is approximately 1.2 times solar, meaning the star has slightly enhanced abundances of heavy elements compared to our Sun. This enhanced metallicity is consistent with the presence of a massive planet, as metal-rich stars are more likely to host gas giants. The distance from Earth is approximately 680 light-years, placing WASP 118b in the moderately distant range for exoplanets. The host star's brightness makes spectroscopic observations feasible with large telescopes. Chapter 4. Atmospheric Considerations. What can we say about WASP 118b's atmosphere, and what might future observations reveal? As of current knowledge, detailed atmospheric characterization of WASP 118b hasn't been extensively published in major studies, though the planet remains on target lists for future observations. Based on its temperature of approximately 1500 to 1600 Kelvin and typical hot Jupiter compositions, we can make informed predictions about what WASP 118b's atmosphere should contain. At 1500 to 1600 Kelvin, the atmosphere is certainly dominated by hydrogen and helium, as these light gases can escape from a planet with 0.514 Jupiter masses. Water vapor should be abundant in gaseous form. Water is one of the most common molecules in giant planet atmospheres and remains gaseous at these temperatures. Carbon monoxide and carbon dioxide are likely present, with their relative abundances depending on atmospheric chemistry and carbon-to-oxygen ratio. Alkaline metals like sodium and potassium should exist in atomic form in the upper atmosphere, creating strong absorption features in optical wavelengths. These features have been detected in many hot Jupiter atmospheres and are among the easiest signatures to observe from ground-based telescopes. At 1500 to 1600 Kelvin, some cloud formation is possible, though less extensive than on cooler planets. Possible cloud materials include silicate condensates, essentially tiny droplets of liquid rock or solid particles of minerals that would be rocks on Earth, metal oxides like titanium oxide and aluminum oxide, and possibly sulfur compounds depending on atmospheric sulfur abundance. The atmospheric dynamics are driven by the intense day-night temperature contrast. Despite constant stellar heating on the day side and no stellar heating on the night side, atmospheric circulation redistributes heat. Supersonic winds likely race around the planet at several kilometers per second, carrying heat from day side to night side. The efficiency of this heat transport affects observable properties like the day-night temperature difference and where the hottest point on the planet is located. Theoretical models predict WASP 118b should have strong atmospheric circulation driven by the stellar radiation gradient. The permanent day side creates a persistent pattern of rising air on the heated hemisphere and sinking air on the cooler night side, with strong eastward winds at the equator. The extreme temperatures also drive vigorous chemistry. Molecules form and break apart based on local temperature and pressure. Carbon might exist as carbon monoxide, carbon dioxide, or methane, depending on conditions. Understanding hot Jupiter chemistry requires considering kinetics, how quickly reactions occur, as well as thermodynamic equilibrium. One possibility is that WASP 118b has a temperature inversion, a region where temperature increases with altitude rather than decreasing. This would occur if compounds in the upper atmosphere efficiently absorb stellar radiation, heating those layers. Whether WASP 118b has an inversion depends on atmospheric composition and the stellar spectrum. Future atmospheric observations could reveal molecular abundances, temperature structure, cloud properties, day-night heat redistribution efficiency, and possibly atmospheric variability indicating weather patterns. Chapter 5. Scientific Significance. What makes WASP 118b scientifically important? WASP 118b's significance lies in its role as a representative example of the hot Jupiter population. Let me explain why studying typical cases matters as much as studying extremes. First, WASP 118b contributes to hot Jupiter population statistics. Understanding planetary populations requires studying both extremes and averages. By characterizing many hot Jupiters across different masses, radii, temperatures, and orbital distances, astronomers identify correlations and patterns. WASP 118b is one data point among hundreds, helping answer questions through statistical analysis. Second, it tests planetary inflation theories. With a density of 0.36 grams per cubic centimeter at 1500 to 1600 Kelvin and receiving substantial stellar flux at 0.051 AU, WASP. 118b sits in the range where theoretical models should reliably predict properties. If models can't explain typical cases like WASP, 118b, they need refinement. Third, WASP. 118b helps calibrate atmospheric models. Theoretical predictions for hot Jupiter atmospheres should accurately match observations for typical planets like WASP. 118b. Discrepancies between predicted and observed properties reveal missing physics that improve models for all planets. Fourth, it represents what we'll find around many stars if we look. Extreme planets are rare by definition. If we want to understand what's common versus exceptional, we need to characterize many typical examples. WASP. 118b helps define the norm against which extremes are compared. Fifth, ground-based discoveries like WASP. 118b demonstrate the continued value of systematic surveys monitoring bright stars. While space missions discover thousands of planets around faint stars, ground-based projects identify bright targets suitable for detailed follow-up. These contributions make WASP 118b valuable not as a headline-grabbing extreme discovery, but as a reliable representative of the hot Jupiter population, helping build comprehensive understanding. Chapter 6. Habitability Context. Let's briefly address habitability for WASP 118b. At temperatures around 1500 to 1600 Kelvin, WASP 118b is far too hot for life as we know it. Water exists only as steam. Organic molecules would be thermally unstable. The intense radiation would sterilize any surface. And as a gas giant, WASP 118b has no solid surface anyway. However, studying hot Jupiters like WASP 118b contributes to astrobiology indirectly. Understanding gas giant migration helps us understand planetary system architecture. Hot Jupiters didn't form where we find them. They migrated inward through disk interactions or planet-planet scattering. This migration can dramatically affect interplanetary systems, potentially ejecting smaller rocky planets or preventing their formation. Atmospheric characterization techniques developed for hot Jupiters will eventually be applied to potentially habitable worlds. Every molecule detected, every cloud characterized advances our capability to study more challenging targets, the smaller, cooler, potentially Earth-like planets where biosignatures might exist. So while WASP 118b itself isn't habitable, the knowledge gained contributes to the broader scientific framework enabling the search for habitable worlds. Chapter 7. Future Research. What's next for studying WASP 118b? Several research directions could advance our understanding. The James Webb Space Telescope could potentially observe WASP 118b as part of broader hot Jupiter atmospheric surveys. JWST's extended wavelength coverage and high sensitivity enable detection of molecular features invisible to other telescopes. For WASP 118b, JWST could detect molecules like water vapor, carbon monoxide, methane, and others, measure atmospheric metallicity, characterize cloud properties, and constrain temperature-pressure profiles. Ground-based high-resolution spectroscopy using current large telescopes or extremely large telescopes expected in the late 2020s could enable detection of individual molecular absorption lines and measurement of atmospheric dynamics through Doppler shifts. Long-term transit timing observations over many years could search for additional planets through gravitational perturbations or detect orbital decay from tidal interactions. Phase curve observations, monitoring the system's brightness continuously as the planet orbits, could reveal how heat is redistributed across the planet. Even without extensive individual observations, WASP 118b contributes to population studies, comparing many hot Jupiters statistically. Chapter 8, Conclusion. Let's recap what we've learned about WASP 118b. WASP 118b is a moderately inflated hot Jupiter discovered in 2014 by the WASP South facility through the transit method and confirmed via radial velocity measurements. With 1.13 Jupiter radii, 0.514 Jupiter masses, and a density of 0.36 grams per cubic centimeter, it represents a typical moderately inflated hot Jupiter experiencing significant stellar heating. Orbiting every 4.05 days at 0.051 AU from an F6 star, WASP 118b experiences extreme conditions with temperatures around 1500 to 1600 Kelvin. The relatively short period makes it valuable for repeated observations and long-term monitoring. What makes WASP 118b significant isn't extreme properties, but its representativeness. It sits within hot Jupiter population distributions, helping define what these planets are typically like. Understanding the average reveals common processes and provides the baseline for comparison. The discovery by the WASP project demonstrates the continued importance of ground-based surveys. While space missions discover thousands of planets, ground-based projects identify bright targets suitable for atmospheric characterization. 680 light-years away, WASP 118b continues its rapid orbit, completing over 90 circuits per Earth year. One hemisphere faces a sun-like star at point-blank range, heated to temperatures where iron would glow. The other knows only darkness, cooled by supersonic winds. Hydrogen and helium dominate this world, compressed to exotic states in the deep interior, extended to tenuous gas in the upper atmosphere. Atmospheric dynamics drive weather patterns unlike anything in our solar system. This planet won't win records for being the hottest, largest, or most unusual hot Jupiter. But that's not its scientific value. WASP 118b matters because it shows us what's typical, defining the population. Every planet we discover and characterize expands our understanding of planetary diversity. The extremes push theories to their limits and generate excitement. The typical cases reveal what's common and test whether models work for representative examples. WASP 118b is one of over 200 WASP discoveries, each contributing to comprehensive understanding of gas giants and planetary systems. For the next planet today, we're diving into K2115b, a super-Earth from the K2 mission. 680 light-years from Earth, a planet 1.7 times Earth's radius orbits its star every 2.4 days. Discovered by NASA's K2 mission, the ingenious second life of the Kepler Space Telescope after its reaction wheels failed. K2115b represents one of hundreds of planets that wouldn't exist in our catalogs if engineers hadn't refused to accept defeat. This is K2115b, a hot super-Earth discovered through persistence and creativity, orbiting too close to its star for habitability, but scientifically valuable for understanding the most common planet type around other stars, a type completely absent from our own solar system. Hey everyone, welcome back to the channel. Today we're exploring K2115b, a super-Earth discovered in 2018 by NASA's K2 mission, the remarkably successful continuation of the Kepler Space Telescope after its primary mission ended due to mechanical failures. K2115b sits at 1.7 Earth radii, placing it in the super-Earth category. Planets larger than Earth but smaller than Neptune, typically ranging from about 1.25 to 2 Earth radii. These planets are the most common type found around other stars, yet our solar system has nothing like them. Understanding why super-Earths are ubiquitous elsewhere, but absent here, is one of the biggest questions in planetary science. With an orbital period of just 2.4 days, K2115b orbits extremely close to its host star, far too close for liquid water or habitability. But this proximity makes it scientifically valuable. Close-in planets transit frequently, allowing repeated observations that characterize their properties precisely. And studying hot super-Earths like K2115b reveals how these planets form, how they retain or lose atmospheres, and what processes shape their evolution. The planet orbits a K-type dwarf star, slightly cooler and smaller than our Sun. K2115 is relatively bright for a K2 target, making follow-up observations feasible for detailed characterization. Though K2115b hasn't been as extensively studied as some other super-Earths around even brighter stars. Discovered during K2 Campaign 17, K2115b exemplifies the mission's success at finding planets around stars across the sky after Kepler's original mission ended. Between 2014 and 2018, K2 observed 19 different fields, discovering hundreds of confirmed planets and thousands of candidates that continue being validated. Today we're going to explore how the K2 mission continued Kepler's legacy after mechanical failures, how K2115b was discovered through transit observations, what its physical characteristics reveal about super-Earths, why studying hot super-Earths matters despite them not being habitable, how K215b compares to other super-Earths and what this reveals, and what future observations might teach us about this and similar planets. Let's discover a super-Earth from Kepler's remarkable second life. Section 1. The K2 mission. K215b exists in our catalogs because engineers refuse to accept that Kepler's mission was over when critical components failed. The original Kepler mission launched in March 2009 with an ambitious goal: stare continuously at about 150,000 stars in a single field in the constellation Cygnus, searching for planets via the transit method. For over 4 years, Kepler was extraordinarily successful, discovering thousands of planet candidates and revolutionizing our understanding of planetary systems. Kepler's success depended on incredibly precise pointing, maintained by 4 reaction wheels, spinning devices controlling spacecraft orientation. The mission was designed to tolerate one-wheel failure, operating with 3 wheels providing sufficient control. In July 2012, reaction wheel number 2 failed. Kepler continued using 3 remaining wheels. But on May 11, 2013, reaction wheel number 4 failed. With only 2 functioning wheels, Kepler couldn't maintain the arc-second level pointing precision required for its primary mission. NASA officially declared the Kepler mission ended in August 2013. But the Kepler engineering team proposed an ingenious solution: use solar radiation pressure, the gentle push of sunlight on the spacecraft, as a virtual 3rd reaction wheel. By orienting along the ecliptic plane and carefully balancing solar pressure with the 2 remaining wheels, they could achieve sufficient pointing stability to continue planet hunting. The catch was that the spacecraft would drift slowly, and every 83 days when solar pressure became too strong, Kepler would need to roll to a new field. Instead of staring at one field forever, K2 would observe different fields for roughly 80 days each, called campaigns, then rotate to new targets. NASA approved the K2 mission concept in May 2014. Campaign 0, a 9-day engineering test in February 2014, proved the concept worked. Campaign 1 began May 30th, 2014, marking K2's official start. Between 2014 and 2018, K2 completed 19 campaigns observing fields distributed around the ecliptic plane. Each campaign monitored tens of thousands of stars, about 20,000 to 30,000 per campaign, building light curves revealing transiting planets. The K2 mission had several advantages over the original Kepler mission. By observing multiple fields, K2 sampled stars across different galactic environments and stellar populations. The fields included many bright nearby stars, excellent for follow-up characterization. and the mission demonstrated that creative engineering can extend spacecraft lifetimes far beyond design specifications. K2's strategy was similar to the original Kepler. Detect periodic dimming in stellar brightness indicating transiting planets, then validate candidates through statistical analysis and follow-up observations. Automated pipelines searched K2 photometry for transit signals. Promising candidates were flagged for validation using techniques distinguishing genuine planets from false positives like eclipsing binary stars. By the mission's end in November 2018, when fuel was exhausted, K2 had discovered over 400 confirmed planets and identified thousands of candidates requiring further validation. Among these discoveries was K2115b, found during Campaign 17 in 2018. Chapter 2. The Discovery. During Campaign 17 from March to May 2018, K2 observed a star cataloged as EPIC 247267267, later designated K2115. The K2 photometry revealed periodic transit signals occurring every 2.4 days. The transit depth was approximately 0.15%, small but clearly detectable above the photometric noise. The transit duration was about 2 hours, consistent with a small planet in a very close orbit around a sun-like star. From these transit observations, astronomers could immediately estimate the planet's radius from how much light was blocked. The preliminary estimate was approximately 1.7 Earth radii, placing the planet in the super-Earth category between Earth-sized and Neptune-sized worlds. However, K2 observations alone couldn't confirm K2115b was a genuine planet or determine its mass. Follow-up observations were essential to validate the discovery and characterize the planet's properties. The discovery team used several validation approaches. Statistical validation assessed the probability that the transit signal came from a planet versus false positive scenarios. By analyzing the transit shape, duration, and regularity alongside stellar properties and a local stellar environment, astronomers calculated that K2115b was very likely a genuine planet rather than a false positive. High-resolution imaging from ground-based telescopes verified K2115 is a single star without close companions creating false transit signals. These observations can detect companion stars that might be invisible to K2's relatively low spatial resolution, but could produce transit-like signals. Spectroscopic observations characterize the host star precisely, measuring its temperature, surface gravity, metallicity, and other properties. Accurate stellar parameters are essential for determining accurate planetary parameters, as the planet size is calculated relative to the star's size. Radial velocity measurements attempted to detect the gravitational wobble induced by the planet's mass. For super-Earths, especially those around relatively faint stars like K2115, radial velocity signals are small, typically just a few meters per second, and challenging to measure with current spectrographs. As a result, K2115b's mass wasn't precisely measured from radial velocity, leaving some uncertainty about its composition and density. K2115b was announced in 2018 as part of papers presenting validated K2 planets from Campaign 17. The planet joined the growing catalog of super-Earths discovered by K2 and the original Kepler mission, contributing to statistical understanding of this planet population. The discovery demonstrates K2's success at finding small planets despite spacecraft limitations. Even with degraded pointing precision compared to the original Kepler mission, K2 could detect super-Earth-sized planets, testament to the engineering creativity that enabled the mission's continuation. Chapter 3. Characteristics of K2115b. Let's examine K2115b's characteristics in detail, because they place it firmly in the super-Earth population at the smaller end of this size range. K2115b is classified as a super-Earth, planets with radii between roughly 1.25 and 2 Earth radii. At 1.7 Earth radii, K2115b sits comfortably in this category, being about 70% larger in diameter than Earth. The radius is well determined from K2 transit observations at 1.7 Earth radii. The mass is uncertain. Radial velocity measurements haven't definitively constrained it, but statistical relationships for planets this size suggest approximately 3 to 6 Earth masses, depending on composition. If K2115b is on the lower end of that mass range, around 3 to 4 Earth masses, it would have a density suggesting rocky composition, possibly with significant water content or a thin atmosphere. If it's on the higher end, around 5 to 6 Earth masses, the lower density would indicate either substantial water or a hydrogen-helium atmosphere. This mass composition ambiguity is common for super-Earths, where radial velocity measurements are challenging. Without precise mass measurements, we can't definitively determine whether K2115b is rocky, water-rich, or has a substantial atmosphere. Very different planetary types with different formation and evolution histories. At 1.7 Earth radii, K2115b sits near the Radius Valley, the observed gap in the planetary radius distribution around 1.5 to 2 Earth radii. This gap is thought to result from atmospheric photoevaporation, stellar radiation stripping atmospheres from planets below a critical mass threshold. K2115b at the upper edge of the valley might have retained an atmosphere or might be rocky, having lost primordial hydrogen-helium. The orbital characteristics are precisely known from K2 observations. K2115b orbits every 2.406 days, about 57.7 hours. The semi-major axis is approximately 0.03 AU, which is about 4.5 million kilometers or 2.8 million miles. To put this in perspective, Mercury orbits the Sun at 0.39 AU. K2115b orbits about 13 times closer to its star than Mercury does to ours. At this distance, the planet is certainly tidally locked with one hemisphere permanently facing the star. The orbital velocity is approximately 160 kilometers per second. The orbital eccentricity is assumed very low, essentially zero, meaning the orbit is circular, typical for planets in such close orbits where tidal forces rapidly circularize initially eccentric orbits. The equilibrium temperature is estimated at approximately 1,000 to 1,100 Kelvin, or about 700 to 800 degrees Celsius. This is far too hot for liquid water. Water exists only as steam at these temperatures. The permanent day side would be even hotter under constant stellar irradiation, while the night side would be cooler, but still extremely hot. The host star K2115 is a K-type dwarf star, cooler and smaller than our Sun, but hotter than M-dwarfs. The stellar mass is approximately 0.75 solar masses, about 3/4 the Sun's mass. The radius is about 0.7 solar radii. The temperature is approximately 4,900 Kelvin, cooler than the Sun's 5,778 Kelvin. The age is estimated at several billion years, indicating a mature main sequence star. The metallicity appears roughly solar, meaning similar abundances of elements heavier than hydrogen and helium compared to the Sun. The distance from Earth is approximately 680 light-years, moderately distant, but within reach of follow-up observations with large telescopes. The host star's brightness at magnitude 13.6 makes spectroscopic observations challenging, but feasible with dedicated telescope time. Chapter 4. The Super-Earth Mystery. What makes K2115b scientifically fascinating is what we don't yet know, and what it represents about the super-Earth population. Super-Earths like K2115b represent one of the biggest mysteries in exoplanet science. They're the most common planet type around other stars, Surveys suggest roughly 30 to 50% of Sun-like stars host planets in this size range. Yet our solar system has nothing like them. We have rocky terrestrial planets up to 1 Earth radius, and gas/ice giants starting at 4 Earth radii, but nothing between. Why are super-Earths so common elsewhere, but absent here? Understanding their nature, rocky versus gaseous, how they form, how they evolve, helps answer this fundamental question about our solar system's architecture. For K2115b specifically, several scenarios are possible. If it's primarily rocky with a thin atmosphere, it might have formed similarly to Earth but accumulated more material. The thin atmosphere could be remnant hydrogen-helium that survived photoevaporation, or a secondary atmosphere outgassed from the interior. If it's a mini-Neptune with substantial hydrogen-helium, it formed by accumulating a rocky core, then capturing gas from the protoplanetary disk. The question becomes, how much hydrogen-helium does it have, and why has it survived billions of years of stellar irradiation at just 0.03 AU? A third possibility is that K2115b is a water world, a planet with a rocky core surrounded by a thick water layer in various phases, with a steam atmosphere on top. Such planets might form beyond the snow line where water ice is abundant, then migrate inward. Distinguishing between these scenarios requires measuring the planet's mass precisely. With both radius and mass, we calculate density, which strongly constrains composition. A density around 4 to 5 grams per cubic centimeter would suggest rocky composition with minimal volatiles. A density around 2 to 3 grams per cubic centimeter would indicate substantial water or thin hydrogen atmosphere. A density around 1 gram per cubic centimeter would confirm significant hydrogen-helium. The position near the radius valley is particularly interesting. If K2115b retained a primordial atmosphere despite being close to its star, this constrains photoevaporation efficiency. If it lost its atmosphere and is rocky, this validates photoevaporation models. Either way, understanding K2115b's composition tests theories about atmospheric retention. The temperature of 1000 to 1100 Kelvin places K2115b in an interesting regime. It's hot enough that water exists only as steam, but cool enough that rock-forming minerals don't vaporize entirely. Atmospheric dynamics would be vigorous, with possible day-night circulation patterns transporting heat from the permanent day side to the night side. Chapter 5. Habitability Assessment. Let's address habitability for K2115b, though the answer is straightforward. At temperatures exceeding 1000 Kelvin, K2115b is far too hot for liquid water on any surface. The planet orbits well inside the habitable zone, which for K2115 would be roughly 0.4 to 0.8 AU. At 0.03 AU, K2115b is about 13 to 27 times closer than the habitable zone's inner edge. At these temperatures, any water exists as steam. Rocky surfaces will be hot enough that some minerals might partially melt. Tidal locking creates extreme temperature contrasts unless atmospheric circulation efficiently redistributes heat. And the intense stellar radiation makes conditions completely inhospitable to life as we know it. However, K2115b's scientific importance for astrobiology is substantial despite its own uninhabitability. Understanding super-Earths generally, how common different types are, whether they typically retain atmospheres, what processes shape their evolution, informs predictions about potentially habitable super-Earths around other stars at more temperate distances. If we can determine whether hot super-Earths like K2115b are rocky or have retained atmospheres, this reveals the threshold for atmospheric retention and helps predict which cooler super-Earths might maintain conditions suitable for life. So while K2115b itself isn't habitable, Studying it contributes essential knowledge to the framework enabling searches for potentially habitable worlds elsewhere. Chapter 6. Scientific Significance. Why does K2115b matter for exoplanet science? K2115b contributes to several research areas. First, super-Earth population statistics. At 1.7 Earth radii, K2115b sits in the size range of the most common planet type. Characterizing many super-Earths reveals whether they're predominantly rocky, gaseous, or diverse. Each additional planet, like K2115b, constrains population statistics. Second, radius valley studies. At 1.7 Earth radii, K2115b sits near the upper edge of the radius valley. Understanding whether planets at this size retained atmospheres versus lost them to photoevaporation tests theoretical models of atmospheric evolution. Third, K-type star planetary systems. K2115 orbits a K-dwarf, intermediate between Sun-like G-stars and cooler M-dwarfs. Understanding planet populations around K-stars reveals how stellar properties influence planetary characteristics and occurrence rates. Fourth, K2 mission legacy. K2115b represents one of hundreds of planets discovered by K2's creative second life. These discoveries demonstrate that mission extensions through innovative engineering can yield enormous scientific returns. Fifth, follow-up target identification. While K2115b hasn't been extensively characterized beyond its initial discovery, it remains in catalogs as a potential target for future atmospheric studies if priorities and telescope availability permit. Chapter 7. Comparative Context. How does K2115b compare to other super-Earths? K2115b at 1.7 Earth radii is fairly typical for the super-Earth population. Many similar planets are known, with sizes ranging from about 1.3 to 2.0 Earth radii and orbital periods from hours to weeks. Some super-Earths are better characterized. For instance, 55 Cancri E at 1.9 Earth radii has been extensively studied with Spitzer and JWST, revealing an atmosphere and possible lava surface. HD 219134b at 1.6 Earth radii has a measured mass indicating rocky composition, and planets in multi-planet systems like those around TRAPPIST-1 provide comparative context within single systems. K2115b represents a more typical case, discovered, validated, radius measured, but not yet extensively characterized with mass measurements or atmospheric observations. This is actually the norm for most exoplanets. We know they exist, we know their sizes and orbits, but detailed characterization awaits future observations or higher priority targets. Comparing K2115b to the population reveals it's neither unusually large nor small for super-Earths, neither extremely hot nor relatively cool, neither around an exceptionally bright star nor an exceptionally faint one. It's representative, which makes it valuable for understanding typical super-Earths rather than exceptional cases. Chapter 8. Future Research. What's next for K2115b? Several research directions could advance understanding. Precise radial velocity measurements would determine mass, enabling density calculation that would resolve whether K2115b is rocky, water-rich, or has a hydrogen atmosphere. This single measurement would answer the planet's fundamental nature. If mass measurements confirm K2115b retained an atmosphere, transmission spectroscopy could detect molecules revealing atmosphere composition. The James Webb Space Telescope could potentially observe K2115b if prioritized, though brighter targets will likely receive preference given limited telescope time. Ground-based, extremely large telescopes in the late 2020s might enable high-resolution spectroscopy, potentially revealing atmospheric properties even for challenging targets like K2115b. Population studies comparing many super-Earths will be as valuable as detailed individual characterizations. By observing dozens of planets like K2115b around different stars, patterns emerge revealing formation and evolution processes that individual observations can't determine. Chapter 9. Conclusion. Let's recap what makes K2115b scientifically important. K2115b is a super-Earth discovered during K2 Campaign 17 in 2018, with 1.7 Earth radii and an estimated mass of 3 to 6 Earth masses, orbiting every 2.4 days at 0.03 AU. K2115b experiences temperatures around 1,000 to 1,100 Kelvin, far too hot for habitability. What makes K2115b special is both its scientific value and symbolic importance. Scientifically, it contributes to understanding super-Earths, the most common planet type around other stars yet absent from our solar system. Every characterized super-Earth helps answer why they're ubiquitous elsewhere but not here. Symbolically, K2115b represents K2 success, a mission that continued discovering planets long after Kepler appeared dead. Engineers found creative solutions when critical components failed, and K2 went on to discover hundreds more planets, including K2115b. 680 light-years away, K2115b continues its rapid orbit, completing 152 circuits per Earth year. One hemisphere faces a K-type dwarf star, heated to over 1,000 Kelvin. The other knows only darkness. Is this world rocky with a thin atmosphere? Is it a mini Neptune with substantial hydrogen-helium? Or is it something in between, a water world with exotic interior structure? We don't know yet. But K2115b exists in our catalogs because a spacecraft refused to die and engineers refused to quit. The story of K2115b reminds us that some discoveries come not just from ambitious missions, but from persistent refusal to accept defeat. When Kepler's reaction wheels failed in 2013, the mission could have ended. Instead, engineers invented a new way to operate, and K2 discovered hundreds more planets, including K2115b. Every planet matters. The famous ones studied extensively teach us details. The typical ones, like K2115b, teach us population properties. Together, they reveal the full spectrum of planetary diversity. Next, let's uncover the mysteries of WASP 139b, a hot Jupiter from the WASP survey. 440 light-years from Earth, a gas giant slightly smaller than Jupiter circles its star every 5 days. Heated to over 1,400 Kelvin by its nearby sun, WASP 139b represents one of hundreds of hot Jupiters discovered by ground-based telescopes, systematically surveying the sky for transiting planets. This is WASP 139b, a world discovered through persistent observation by the Wide-Angle Search for Planets project, confirmed through follow-up measurements, and study to understand how gas giants behave under extreme stellar heating. It's not the most extreme hot Jupiter, but it exemplifies how systematic ground-based surveys continue contributing essential discoveries to exoplanet science. A hot Jupiter discovered in 2015 by the Wide-Angle Search for Planets project, one of the most successful ground-based exoplanet surveys that has transformed our understanding of planetary diversity. WASP 139b might not grab headlines like the most extreme discoveries, the hottest planets, the largest planets, or those in habitable zones. But it represents something equally important, a typical hot Jupiter that helps define what these planets are actually like across the galaxy. By studying many hot Jupiters like WASP 139b, planets with moderate properties, typical orbits, representative characteristics, we build the comprehensive picture needed to understand gas giant physics and planetary system architecture. discovered through the transit method by WASP South in South Africa and confirmed through radial velocity follow-up observations. WASP 139b orbits a relatively bright star, making it accessible for atmospheric characterization and detailed study. It joins over 200 WASP discoveries that have transformed our understanding of how planetary systems form and evolve. The host star, WASP 139, is a G-type star similar to our Sun, slightly cooler and less massive, but recognizably solar-like. At magnitude 11, it's accessible to moderate-sized telescopes, enabling follow-up observations that characterized both star and planet precisely. With an orbital period of 5.2 days, WASP 139b completes about 70 orbits per Earth year. At this close distance of 0.062 EU, about 15 times closer than Mercury orbits the Sun, the planet experiences extreme temperatures exceeding 1400 Kelvin. These conditions make WASP 139b unsuitable for life as we know it, but scientifically valuable for understanding atmospheric physics under extreme stellar radiation. Today we're going to explore how the WASP project operates and why it's been so successful at finding transiting planets, how WASP 139b was discovered and confirmed as a genuine planet, what its physical characteristics tell us about hot Jupiter properties, what we can infer about its atmosphere despite limited direct observations, why studying typical hot Jupiters advances planetary science, and what future observations might reveal about this distant world. Let's discover what ground-based surveys continue teaching us about planetary diversity. Chapter 1. The Discovery. Between approximately 2007 and 2014, WASP South accumulated observations of star cataloged as 1SWASP J050554.57-3227444.9, later designated WASP 139. The automated analysis pipeline detected periodic transit signals occurring every 5.2 days. The dimming was approximately 1.2%. A substantial signal indicating a planet roughly Jupiter-sized, transiting a Sun-like star. The transit duration was about 3 hours, consistent with a close orbit around a main sequence star. From these transit observations, astronomers could immediately estimate several properties. The planet size, determined from how much light was blocked, was approximately 0.8 Jupiter radii, about 20% smaller than Jupiter. The orbital period of 5.2 days indicated a very close orbit, and the regularity of the transits suggested the orbit was likely circular, as tidal forces rapidly circularize orbits at such short distances. However, detecting a transit signal alone doesn't confirm a planet. Various false positive scenarios can mimic planetary transits, including eclipsing binary stars, hierarchical triple star systems, or background eclipsing binaries blended with the target star's light. Ruling out these alternatives requires comprehensive follow-up observations. For WASP 139b, confirming the planet required several types of follow-up observations conducted by the Discovery team. High-resolution imaging from large ground-based telescopes verified that WASP 139 is a single star without close companions that could create false signals. These observations could detect companion stars separated by less than 1 arc-second, closer than WASP's cameras could resolve. Spectroscopic observations from precision spectrographs characterized the host star in detail. By analyzing the star's spectrum, astronomers measured its temperature at approximately 5,700 Kelvin, very similar to the Sun's 5,778 Kelvin. The surface gravity indicated it's a main sequence star, and the metallicity showed roughly solar abundances of heavy elements. Radial velocity measurements from precision spectrographs detected the gravitational wobble induced by the planet's mass. As WASP 139b orbits, its gravity pulls the star slightly, causing the star to move toward and away from us. This motion creates a Doppler shift in the star's spectral lines. The radial velocity measurements measured WASP-139b's mass at approximately 0.12 Jupiter masses, or about 38 Earth masses. This is significantly less massive than Jupiter at 318 Earth masses, making WASP-139b a relatively low-mass hot Jupiter, closer to Saturn's 95 Earth masses than Jupiter's mass. Combined with a radius of 0.8 Jupiter radii from transits, this gives a density of approximately 0.25 grams per cubic centimeter, significantly less dense than Jupiter's 1.33 grams per cubic centimeter. This low density indicates substantial inflation from stellar heating, a common characteristic of close-in gas giants. WASP-139b was announced in 2015 in a paper presenting multiple WASP discoveries. The planet's properties, moderately sized, low mass, inflated hot Jupiter orbiting a bright star, made it scientifically interesting and accessible for future atmospheric studies, though not as high priority as some larger planets around even brighter stars. Chapter 2. Characteristics of WASP-139b. Let's examine WASP-139b's characteristics in detail, because they place it in an interesting region of hot Jupiter parameter space. WASP-139b is classified as an inflated hot Jupiter, a gas giant in a very close orbit with significant radius expansion from stellar heating. The physical characteristics are well determined from combined transit and radial velocity observations. The radius is 0.8 Jupiter radii, making it about 20% smaller in diameter than Jupiter. The mass is 0.12 Jupiter masses, or about 38 Earth masses, roughly 40% of Saturn's mass. The density is approximately 0.25 grams per cubic centimeter. This extremely low density, about 1/5 Jupiter's density, indicates significant inflation. WASP-139b is expanded beyond what you'd expect for a cold gas giant of this mass. The inflation represents the balance between gravitational forces trying to compress the planet and stellar heating, preventing full contraction. The surface gravity is approximately 0.23 times Jupiter's gravity, or about 6/10 Earth's gravity. This weak gravity compared to Jupiter affects atmospheric properties. Lower gravity creates a larger atmospheric scale height, making atmospheric features potentially more prominent in spectroscopic observations if they can be detected. Inside WASP-139b, theoretical models predict a structure typical of inflated hot Jupiters. A rocky or icy core, perhaps 5 to 10 Earth masses, surrounded by layers of hydrogen and helium heated by the nearby star. The inflation suggests stellar energy is penetrating deep into the atmosphere, preventing the planet from contracting to the smaller size it would naturally have at Jupiter's distance from the Sun. The orbital characteristics place WASP-139b among typical hot Jupiters. The orbital period is 5.2 days, about 125 hours. The semi-major axis is 0.062 AU, approximately 9.3 million kilometers or 5.8 million miles. Mercury orbits the Sun at 0.39 AU, so WASP-139b orbits about 6 times closer to its star than Mercury does to ours. This close distance means the planet is certainly tidally locked with one hemisphere permanently facing the star. The orbital velocity is approximately 110 kilometers per second. The orbital eccentricity is very low, essentially zero, meaning the orbit is circular, typical for close-in planets where tidal forces rapidly circularize orbits. The equilibrium temperature is estimated at approximately 1400 Kelvin on the day side, or about 1100 degrees Celsius or 2000 degrees Fahrenheit. This is hot. Water would be steam, many metals would vaporize, but not as extreme as ultra-hot Jupiters exceeding 2500 Kelvin. At these temperatures, atmospheric dynamics are vigorous. Supersonic winds likely race around the planet at several kilometers per second, transporting heat from the permanent day side to the night side. Despite this heat redistribution, the day-night temperature difference probably exceeds several hundred Kelvin. The host star WASP 139 is a G-type star similar to our Sun. The stellar mass is approximately 0.9 solar masses, about 10% less massive than the Sun. The radius is 0.9 solar radii. The temperature is approximately 5,700 Kelvin, very close to the Sun's temperature. The age is estimated at several billion years, indicating a mature, main-sequence star similar in evolutionary state to our Sun. The metallicity is approximately solar, meaning similar abundances of heavy elements. The distance from Earth is approximately 440 light-years, moderately distant, but close enough that detailed observations are feasible with large telescopes. The host star's brightness at magnitude 11 makes spectroscopic observations challenging but possible with dedicated telescope time. Chapter 3. Atmospheric Considerations. What can we infer about WASP 139b's atmosphere despite limited direct observations? As of current knowledge, detailed atmospheric characterization of WASP 139b through transmission spectroscopy or emission spectroscopy hasn't been extensively published. However, based on its temperature, mass, and radius, we can make informed predictions about atmospheric properties. At approximately 1400 Kelvin and with a mass of 0.12 Jupiter masses, WASP 139b's atmosphere is certainly dominated by hydrogen and helium. The planet's gravity is sufficient to retain these light gases despite heating. Water vapor should be abundant in gaseous form at these temperatures. Carbon monoxide and carbon dioxide are likely present, with their relative abundances depending on atmospheric chemistry and carbon-to-oxygen ratio. Alkali metals like sodium and potassium should exist in atomic form in the upper atmosphere, potentially creating strong absorption features in optical wavelengths. At 1400 Kelvin, some cloud formation is possible, though less extensive than on cooler planets. Possible cloud materials include silicate condensates, tiny droplets or particles of rock-forming minerals, and metal oxides like titanium oxide and aluminum oxide. The extremely low density of 0.25 grams per cubic centimeter and corresponding weak surface gravity create a very extended atmosphere with large-scale height. This makes WASP 139 be potentially favorable for atmospheric characterization if observations are attempted, because atmospheric features would be more prominent than for higher gravity planets. The atmospheric dynamics are driven by intense day-night temperature contrast. Models predict strong equatorial jet streams, vigorous vertical convection, and efficient heat transport from day side to night side, though not efficient enough to completely eliminate temperature differences. Whether WASP 139b has a temperature inversion, where temperature increases with altitude in some atmospheric layers, depends on atmospheric composition and opacity. Certain molecules like titanium oxide and vanadium oxide can create inversions by efficiently absorbing stellar radiation. But whether they exist in the observable atmosphere depends on temperature-pressure profiles and atmospheric mixing. Chapter 4. Scientific Significance. What makes WASP 139b scientifically important despite not being extensively studied? WASP 139b's significance lies primarily in its contribution to hot Jupiter population statistics and its role demonstrating ground-based survey success. First, WASP 139b contributes to understanding planetary inflation. With a density of 0.25 grams per cubic centimeter at 1400 Kelvin and receiving substantial stellar flux at 0.062 AU, WASP 139b sits in a regime where theoretical models should reliably predict properties. Testing whether models accurately reproduce observed inflation helps validate or refine theories. Second, It represents the low mass end of hot Jupiter population. Most discovered hot Jupiters have masses between 0.5 and 3 Jupiter masses. WASP 139b at 0.12 Jupiter masses, closer to Saturn's mass, explores what happens at lower masses where atmospheric structure and dynamics might differ from typical Jupiters. Third, WASP 139b demonstrates continued ground-based survey value. While space missions discover thousands of planets, ground-based projects like WASP identify bright targets suitable for follow-up, including atmospheric characterization that requires bright host stars. Fourth, it provides data for comparative studies. By observing many hot Jupiters across different masses, radii, temperatures, and stellar properties, astronomers identify correlations and patterns revealing formation and evolution processes. Fifth, the low surface gravity makes WASP 139 be potentially favorable for atmospheric observations if prioritized. The extended atmosphere with large-scale height could reveal composition more readily than higher gravity planets. Chapter 5. Comparative Context. How does WASP 139b compare to other hot Jupiters? WASP 139b sits at the lower mass end of the hot Jupiter population. With 0.12 Jupiter masses, it's less massive than most hot Jupiters, but more massive than hot Neptunes. The low mass combined with moderate radius creates very low density and weak gravity, characteristics shared by other inflated hot Jupiters, but more pronounced in WASP 139b. The orbital period of 5.2 days is fairly typical for hot Jupiters. The temperature of 1400 Kelvin is moderate, significantly cooler than ultra-hot Jupiters, exceeding 2500 Kelvin, but hotter than warm Jupiters at less than 1000 Kelvin. Compared to extensively studied hot Jupiters like HD 209458b, WASP 12b, or WASP 121b, WASP 139b hasn't received as much observational attention, primarily because other targets offer either brighter host stars, more extreme properties generating greater scientific interest, or better accessibility for specific observing programs. However, WASP 139b represents typical properties for a significant fraction of the hot Jupiter population: moderately inflated, moderate temperature, orbiting a sun-like star at typical hot Jupiter distances. Understanding typical cases is as important as studying extremes for comprehensive population understanding. Chapter 6. Habitability Context. Let's briefly address habitability, though for WASP 139b the answer is straightforward. At temperatures around 1400 Kelvin, WASP 139b is far too hot for life as we know it. Water exists only as steam. Organic molecules are thermally unstable. The intense radiation would sterilize any surface. And as a gas giant, WASP 139b has no solid surface, just increasingly dense layers of hydrogen and helium. However, studying hot Jupiters like WASP 139b contributes to astrobiology indirectly. Understanding gas giant migration helps us understand planetary system architecture. Hot Jupiters migrated inward after formation, potentially affecting interplanetary systems where habitable terrestrial planets might exist. Additionally, atmospheric characterization techniques developed for hot Jupiters eventually apply to potentially habitable worlds. Every successful atmospheric detection, every model improvement, every technique refinement advances our capability for studying more challenging targets where biosignatures might exist. So while WASP 139b itself isn't habitable, knowledge gain contributes to the broader framework enabling searches for habitable worlds and life beyond Earth. Chapter 7. Future Research. What's next for studying WASP 139b? Several research directions could advance understanding, though WASP 139b likely won't be highest priority given limited telescope time and brighter targets. The James Webb Space Telescope could potentially observe WASP 139b as part of broader hot Jupiter atmospheric surveys. JWST's capabilities might detect molecular features revealing atmospheric composition, though brighter targets will likely receive preference. Ground-based high-resolution spectroscopy using current or future extremely large telescopes might detect individual molecular lines through their Doppler signatures, revealing atmospheric composition and dynamics. Long-term transit timing observations over years might detect additional planets through gravitational perturbations or measure orbital decay from tidal interactions. The short orbital period makes WASP 139b sensitive to tidal effect detectable over decades. Phase curve observations monitoring brightness continuously as the planet orbits could reveal heat redistribution efficiency and day-night temperature contrasts, though this requires substantial telescope time. Even without extensive individual observations, WASP 139b contributes to population studies comparing many hot Jupiters statistically to identify trends and test theories across large samples. Chapter 8, Conclusion. Let's recap what we've learned about WASP 139b. WASP 139b is an inflated hot Jupiter discovered in 2015 by WASP South through the transit method and confirmed via radial velocity measurements. With 0.8 Jupiter radii, 0.12 Jupiter masses, and a density of 0.25 grams per cubic centimeter, it represents a low-mass, highly inflated hot Jupiter experiencing significant stellar heating. Orbiting every 5.2 days at 0.062 AU from a Sun-like star, WASP 139b experiences temperatures around 1400 Kelvin. The extremely low density and weak surface gravity create an extended atmosphere that could be favorable for spectroscopic characterization if observations are prioritized. What makes WASP 139b significant isn't extreme properties, but its role as a representative example of the hot Jupiter population, particularly the lower mass, highly inflated subset. Understanding typical cases like WASP 139b helps define population norms and provide context for interpreting more extreme examples. The discovery by WASP demonstrates the continued importance of ground-based surveys monitoring bright stars for transiting planets, complementing space missions by identifying targets suitable for detailed follow-up. 440 light-years away, WASP 139b continues its rapid orbit, completing about 70 circuits per Earth year. One hemisphere faces a Sun-like star, heated to 1400 Kelvin. The other knows only darkness, cooled by supersonic winds. Hydrogen and helium dominate this inflated world, expanded to densities far less than Jupiter despite being closer in size. The planet's low mass and weak gravity create an extended atmosphere where molecules might reveal themselves to our telescopes. If we look, this planet won't win records for being the hottest, largest, or most unusual hot Jupiter, but it represents something valuable, a typical example helping us understand what hot Jupiters are generally like across the galaxy. Every discovered and characterized exoplanet expands our understanding of planetary diversity. The extremes push our theories to their limits and generate public excitement. The typical cases like WASP 139b reveal what's common and test whether models work for representative examples. WASP 139b is one of over 200 WASP discoveries, each contributing to comprehensive understanding of gas giants, planetary system architecture, and the incredible variety of worlds orbiting stars throughout our galaxy. Our next world today is truly special. TOI 451b, a young sub-Neptune in a multi-planet system. 400 light-years from Earth, a planetary system barely 120 million years old orbits a star still in its youth. The system hosts at least 3 planets, including TOI 451b. a subneptune about twice Earth's size, completing an orbit every 1.9 days. This system is so young that dinosaurs roamed Earth when its host star was forming. This is TOI 451b, a planet discovered by NASA's TESS mission in 2021 that offers a rare window into planetary system evolution. By studying planets this young, astronomers observe worlds still in the process of atmospheric evolution, revealing how planets change during their first 100 million years. Processes impossible to observe in mature systems billions of years old. Hey everyone, welcome back to the channel. Today we're exploring TOI 451b, a subneptune discovered in 2021 by NASA's Transiting Exoplanet Survey satellite, part of a remarkable multi-planet system orbiting one of the youngest stars known to host transiting planets. Before we dive in, I need to clarify an important point. TOI 451b is not a super-Earth, as sometimes listed in preliminary databases. At approximately 2 Earth radii, it's classified as a subneptune or mini-Neptune, planets in the 2 to 4 Earth radii range that likely have substantial hydrogen-helium atmospheres rather than being primarily rocky. This distinction matters because subneptunes and super-Earths have fundamentally different compositions, formation histories, and evolution pathways. What makes TOI 451b and its siblings extraordinary is their youth. The host star TOI 451 is only about 120 million years old. For comparison, the Sun is 4.6 billion years old, making TOI 451 roughly 40 times younger. At this age, planets are still evolving rapidly. Atmospheres are being lost to photoevaporation. Orbits may still be migrating. The system provides a snapshot of planetary adolescence. TOI 451 is a K-type dwarf star, cooler and smaller than the Sun. And remarkably, it's a member of the Passevenus stellar stream, a group of young stars moving through space together. This association allows precise age determination, making TOI 451's planets among the few young planets with well-constrained ages. The system hosts at least 3 confirmed planets designated TOI 451b, C, and D, all between roughly 2 and 4 Earth radii, all in very close orbits with periods under 12 days. This compact, multi-planet system around a young star provides unique insights into how planetary systems form and evolve during their first 100 million years. Today we're going to explore how TESS discovers planets through transit observations, how TOI 451b and its siblings were identified and validated, what their physical characteristics reveal about subneptune formation, why studying young planetary systems matters for understanding evolution, how TOI 451b compares to other subneptunes, and what this reveals about atmospheric retention, and what future observations might teach us about these young worlds. Let's discover a planetary system in its adolescence. Chapter 1. The TESS Mission. TOI 451b was discovered by TESS, the Transiting Exoplanet Survey satellite, NASA's mission to find planets around the nearest and brightest stars. TESS launched in April 2018 with a focused mission: survey the entire sky, searching for transiting planets around stars bright enough for detailed follow-up characterization. Unlike Kepler, which stared at one field containing mostly faint distant stars, TESS surveys the whole sky, focusing on nearby bright stars. TESS operates using 4 wide-field cameras that together observe large sections of sky for approximately 27 days at a time, called sectors. During each sector, TESS continuously monitors hundreds of thousands of stars, measuring their brightness every 2 minutes for priority targets and every 30 minutes for full-frame images. The mission divides the sky into sectors arranged in 2 hemispheres. During its initial 2-year primary mission, TESS observed 13 sectors in the southern hemisphere during year 1, then 13 sectors in the northern hemisphere during year 2. The mission has since been extended, re-observing many sectors and discovering additional planets. TESS's strategy differs from Kepler's in crucial ways. By observing the entire sky rather than one field, TESS discovers planets around stars distributed across the sky rather than concentrated in one region. And by targeting nearby bright stars, TESS identifies planets perfect for follow-up atmospheric characterization with JWST and ground-based telescopes. The transit method TESS uses is straightforward. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of starlight, creating a periodic dimming. By detecting these regular dips in brightness, TESS identifies candidate planets designated with TOI numbers, TESS objects of interest. However, TESS observations alone can't confirm planets. Follow-up observations validate candidates and measure planetary properties. Ground-based telescopes conduct additional photometry confirming transits. High-resolution imaging rules out contaminating stars. Spectroscopy characterizes host stars precisely. And for some targets, radial velocity measurements determine planetary masses. TOI 451 caught TESS's attention during Sector 4 in October-November 2018. The star showed multiple periodic transit signals indicating not just one planet, but several, making it immediately interesting as a multi-planet system. Chapter 2. The Discovery. During Sector 4, TESS observed TOI 451, cataloged as TEEP C94986-319 and also known as CD 381467, detecting multiple transit signals. The TESS photometry revealed 3 distinct periodic signals. The strongest signal repeated every 1.86 days with a transit depth of about 0.15%. A second signal occurred every 9.2 days with similar depth. A third signal appeared every 16.3 days, also consistent with a transiting planet. These signals suggested a compact, multi-planet system with 3 sub-Neptune-sized planets in very close orbits. From the transit depths and known stellar properties, preliminary radius estimates were approximately 2 to 3 Earth radii for all 3 planets, clearly in the sub-Neptune size range. The Discovery team conducted extensive follow-up observations to validate these planets and characterize the system. High-resolution imaging from multiple facilities, including the Gemini Observatory verified TOI 451, is a single star without close companions that could create false signals. Spectroscopic observations characterized TOI 451 in detail. The star's spectrum revealed its AK3 dwarf with temperature approximately 4,700 Kelvin. The stellar parameters indicated age around 120 million years, very young for a planet host. Crucially, astronomers identified TOI 451 as a member of the Pisces of Nass stellar stream, a group of young stars born together and moving through the galaxy with similar velocities. This association provides strong age constraints because all stream members formed from the same molecular cloud approximately 120 million years ago. Additional TESS observations from later sectors provided more transit data, refining orbital parameters and confirming the periodic signals. Ground-based photometry from multiple observatories conducted follow-up transit observations with better time resolution, confirming the TESS detections. Radial velocity observations attempted to measure planetary masses through stellar wobbles. However, young stars like TOI 451 are magnetically active with spots and flares, creating radial velocity noise that makes precise mass measurements challenging. As a result, the masses of TOI 451's planets remain uncertain, estimated from statistical relationships, but not directly measured. The discovery was announced in January 2021 in a paper published in the Astronomical Journal. The paper presented all 3 planets, TOI 451b, C, and D, as a validated young multi-planet system offering unique opportunities to study planetary evolution. TOI 451b as the innermost planet with the shortest period became the system's designation B planet. Its proximity to the star makes it particularly interesting for studying atmospheric evolution in young planets experiencing intense stellar irradiation. Chapter 3: Characteristics of TOI 451b. Let's examine TOI 451b's characteristics. Keeping in mind, these measurements have uncertainties given the challenges of characterizing young systems. TOI 451b is classified as a subneptune or mini-Neptune, planets with radii between approximately 2 and 4 Earth radii. At roughly 2 Earth radii, TOI 451b sits at the smaller end of this range, near the boundary with large super-Earths. The radius is estimated at approximately 2 Earth radii from test transit observations. The mass is uncertain, not directly measured from radial velocity due to stellar activity, but estimated at around 3 to 6 Earth masses based on mass-radius relationships for subneptunes. If we assume a mass around 4 to 5 Earth masses, the density would be approximately 2 to 3 grams per cubic centimeter, significantly less than Earth's 5.5 grams per cubic centimeter. This lower density suggests TOI 451b isn't purely rocky, but has either substantial water content or, more likely, a hydrogen-helium atmosphere comprising 10 to 20% of the planet's mass. The orbital characteristics are precisely measured from transit timing. TOI 451b orbits every 1.858 days, about 44.6 hours. The semi-major axis is approximately 0.028 AU, which is about 4.2 million kilometers or 2.6 million miles. For perspective, Mercury orbits the Sun at 0.39 AU. TOI 451b orbits roughly 14 times closer to its star than Mercury does to ours. At this distance, the planet is certainly tidally locked with one hemisphere permanently facing the star. The orbital eccentricity is very low, essentially zero, meaning the orbit is circular, typical for close-in planets where tidal forces rapidly circularize orbits. The equilibrium temperature is estimated at approximately 850 Kelvin, or about 577 degrees Celsius. This is hot, far too hot for liquid water, but not as extreme as ultra-hot planets exceeding 1500 Kelvin. At 120 million years old, TOI 451b is in a critical evolutionary phase. At this age, photoevaporation from intense stellar radiation, especially X-ray and ultraviolet emission from the young active star, is actively removing atmospheric hydrogen. Whether TOI 451b will retain its atmosphere or lose it over the next few billion years depends on its mass and the strength of photoevaporation. The host star TOI 451 is AK3 dwarf with approximately 0.9 solar masses, 0.84 solar radii, and temperature around 4,700 Kelvin. At 120 million years old, the star is much more active than the Sun, producing frequent flares and intense X-ray/UV radiation that drives atmospheric escape on close-in planets. The distance from Earth is approximately 400 light-years, moderately distant, but accessible for follow-up observations. The host star's brightness at magnitude 9.8 makes it feasible for detailed spectroscopic observations, though stellar activity complicates measurements. Chapter 4: The Multi-Planet System. TOI 451b exists within a compact multi-planet system that provides crucial context for understanding its formation and evolution. The TOI 451 system hosts at least 3 confirmed planets, all subneptunes between roughly 2 and 4 Earth radii. TOI 451b, approximately 2 Earth radii, 1.86 day period, 0.028 AU. TOI 451c, approximately 3 Earth radii, 9.2 day period, approximately 0.08 AU. TOI 451d, approximately 4 Earth radii, 16.3-day period, approximately 0.12 EU. This architecture, multiple sub-Neptunes in compact, close-in configurations, is common around both young and mature stars. The system resembles many multi-planet systems discovered by Kepler and TESS, suggesting this architectural pattern forms early and often survives billions of years. However, the youth of TOI 451 system makes it special. These planets are currently experiencing intense photoevaporation that may significantly alter their sizes over the next few billion years. TOI 451b, being closest to the star, experiences the most intense irradiation and may lose substantial atmosphere. Interestingly, all 3 planets sit above the radius valley. The observed gap in the planetary radius distribution around 1.5 to 2 Earth radii. This suggests all 3 have retained hydrogen-helium atmospheres so far, though TOI 451b may be in the process of losing its envelope. The compact spacing and near-circular orbits suggest the planets didn't undergo violent dynamical interactions, but rather formed in relatively stable configurations, possibly migrating gently inward or forming in situ near their current locations. Chapter 5: Atmospheric Evolution. What makes TOI 451b scientifically valuable is its youth and what this reveals about atmospheric evolution. At 120 million years old, TOI 451b is young enough that atmospheric evolution processes are still actively shaping the planet. Photoevaporation, the process where high-energy stellar radiation heats and escapes the upper atmosphere, is currently removing hydrogen from TOI 451b's atmosphere. Young stars like TOI 451 emit much more X-ray and ultraviolet radiation than mature stars, driving particularly strong photoevaporation. During the first few hundred million years, this process can completely strip hydrogen-helium envelopes from planets below a critical mass threshold, transforming sub-Neptunes into rocky cores. TOI 451b's current size of 2 Earth radii and position just above the radius valley suggests it's right at the boundary where atmospheric retention versus loss is determined. If its mass is sufficiently high, perhaps above 5 Earth masses, it might retain atmosphere indefinitely. If its mass is lower, it might lose its envelope over the next billion years, eventually becoming a rocky super-Earth. Observations of TOI 451b today provide a snapshot of this process in action. By comparing TOI 451b to older sub-Neptunes of similar size and studying how its atmosphere responds to stellar irradiation, we can test theoretical models of photoevaporation and predict which planets retain atmospheres long-term. The system's 3 planets at different orbital distances also provide comparative context. TOI 451c and d, farther from the star, experience less intense irradiation. Comparing atmospheric retention across all 3 planets reveals how photoevaporation efficiency depends on orbital distance. Chapter 6: Habitability Assessment. Let's address habitability for TOI 451b. At temperatures around 850 Kelvin and orbiting at 0.028 AU, TOI 451b is far too hot for liquid water or life as we know it. The planet orbits well inside any habitable zone, experiencing temperatures where water exists only as steam. Additionally, as a sub-Neptune with likely substantial hydrogen-helium atmosphere, TOI 451b probably has no solid surface, just increasingly dense gas transitioning to exotic states at depth. And even if a surface existed, the intense stellar irradiation and frequent flares from the young active star would make conditions inhospitable. However, TOI 451b's scientific importance for astrobiology is substantial despite not being habitable itself. Understanding how planetary atmospheres evolved during the first 100 million years, the critical phase when photoevaporation is most intense, helps predict which planets around other stars will retain conditions potentially suitable for life billions of years later. If we can determine what factors allow planets like TOI 451b to retain or lose atmospheres, we can better assess which exoplanets around mature stars might have maintained stable atmospheres conducive to habitability throughout their histories. Chapter 7. Scientific Significance. Why does TOI 451b matter for exoplanet science? TOI 451b contributes to several research areas. First, young planet characterization. Only a few dozen planets are known around stars younger than a few 100 million years. TOI 451b is among the youngest transiting planets with well-determined properties, providing rare observational constraints on planetary system evolution. Second, atmospheric evolution studies. TOI 451b is currently experiencing photoevaporation. Observing atmospheric mass loss in real-time tests theoretical models and reveals how efficiently stellar radiation strips planetary atmospheres. Third, radius valley formation. Understanding whether TOI 451b will cross the radius valley, transitioning from sub-Neptune to super-Earth by losing its atmosphere, directly tests photoevaporation as the mechanism carving the gap. Fourth, multi-planet system architecture. The TOI 451 system's 3 planets provide comparative context for understanding how formation location and stellar distance affect planetary outcomes. Fifth, test mission success. TOI 451 demonstrates TESS's capability to find scientifically valuable multi-planet systems around bright nearby stars, identifying targets perfect for detailed follow-up. Chapter 8. Future Research. What's next for studying TOI 451b? Several research directions could advance understanding. Precise mass measurements through improved radial velocity techniques accounting for stellar activity would determine density, constraining whether TOI 451b is primarily rocky with thin atmosphere or has substantial hydrogen-helium envelope. Atmospheric characterization through transmission spectroscopy could detect atmospheric escape signatures, revealing photoevaporation in action. The James Webb Space Telescope could potentially observe TOI 451b, those stellar activity and relatively faint host star present challenges. Long-term monitoring over decades might detect atmospheric changes as photoevaporation removes hydrogen, though detecting such evolution requires extraordinary precision maintained over many years. Comparative studies of all 3 TOI 451 planets would reveal how photoevaporation efficiency varies with orbital distance. Testing models of atmospheric evolution. Identifying additional young multi-planet systems for comparison would determine whether TOI 451's architecture is typical or unusual for young systems, revealing how planetary systems evolve from youth to maturity. Chapter 9. Conclusion. Let's recap what makes TOI 451b scientifically important. TOI 451b is a sub-Neptune approximately 2 Earth radii, orbiting every 1.86 days at 0.028 AU from a young K-dwarf star only 120 million years old. Part of a 3-planet system, TOI 451b provides rare observational access to planetary adolescence, the critical phase when atmospheric evolution is most dramatic. At this age, photoevaporation is actively removing atmospheric hydrogen. Whether TOI 451b retains its atmosphere or loses it over the next billion years tests fundamental theories about planetary evolution and determines which planets maintain conditions that could eventually support life. Discovered by TESS in 2021, TOI 451b exemplifies the mission's success at finding scientifically valuable planets around bright nearby stars, identifying systems perfect for long-term study as they evolve. 400 light-years away, TOI 451b races around its young star, completing nearly 200 orbits per Earth year. Hydrogen escapes to space, carried away by intense stellar radiation. The planet's atmosphere is being sculpted by processes we can observe in real time, processes that shape the planets of our own solar system billions of years ago. This world offers a window into planetary youth, an age when dinosaurs were just emerging on Earth, when the TOI 451 system was forming from collapsing gas clouds. By studying TOI 451b today, we witness planetary evolution we can't observe in mature systems, revealing how planets change during their first 100 million years. The story of TOI 451b reminds us that planets aren't static. They evolve dramatically over time, especially during youth when stellar radiation is most intense. Understanding this evolution helps us interpret the mature planets we observe today and predict which young planets will survive atmospheric loss to potentially host life billions of years hence. What do you think TOI 451b will look like in a billion years? Will it retain its atmosphere or become a rocky core? Share your thoughts in the comments. Thank you for watching until the end. It truly means the world to me. If you enjoyed this video, please give it a like and hit that subscribe button for more cosmic adventures. I'd love to hear your thoughts. What was your favorite exoplanet we discussed today? And which one should I dive into next? Your suggestions help shape our journey together. I'll see you tomorrow for more explorations, and thanks again for tuning in.